Hello there, and welcome to Life Beyond Seen, where curiosity slows down a little, science stays gentle, and the edges of the world become places to quietly explore before sleep. Tonight, we're heading far north, past the busy shipping lanes, past the last scattered towns, into a region that still resists full understanding. The Arctic, vast, cold, often silent, and surprisingly full of unanswered questions. It may look empty on a map, mostly white space and frozen ocean, but that impression can be misleading. Some of the least observed ecosystems on Earth sit under that ice, in water so cold it numbs equipment, in darkness that lasts for months, in conditions that discourage even the most determined explorers. The idea for tonight's journey is simple. We're going to consider how the Arctic, even in an age of satellites and underwater drones, still hides creatures no human has ever seen directly, not photographed, not sampled, not recorded in any scientific catalogue. Real organisms, very likely alive right now, going about their routines beneath ice shelves, inside deep polar waters, or locked within frozen environments where observation remains difficult. It isn't speculation in the dramatic sense. It's simply how biology works. Wherever exploration is incomplete, undiscovered species tend to exist. And before we settle into this, I'm curious for a quiet moment. Where are you listening from right now, and what time is it where you are? It's always slightly amusing to think about. A discussion about one of the coldest, darkest places on Earth, yet people tune in from warm bedrooms, late buses, early mornings, different seasons entirely. The Arctic itself experiences long stretches where the sun barely rises, or doesn't rise at all, while somewhere else the day is bright and ordinary. If you find this kind of calm, scientific wandering helpful for winding down, or simply interesting enough to keep playing softly in the background, a like or subscription helps the channel keep making these slow explorations. Nothing urgent about it, just a small way to keep this quiet corner going for anyone else who enjoys thoughtful science without the rush. So let's ease into it. Picture the Arctic not as a flat sheet of ice, but as a layered environment, sea ice on top, shifting constantly. Beneath that, frigid seawater, with currents that move slowly but persistently. Below that, deeper basins where sunlight never reaches. Add coastlines, glaciers, seasonal meltwater, permafrost soils, and microbial habitats locked in frozen ground. Suddenly it's less of a blank white space, and more of a complex, largely underexplored biological network. One reason the Arctic still hides unknown creatures is straightforward logistics. Access is difficult. Ships require reinforced hulls. Aircraft operations depend heavily on weather windows. Equipment fails more easily in extreme cold. Electronics drain faster. Mechanical parts stiffen. Even simple tasks like collecting water samples become complicated when temperatures threaten both gear and researchers. The cold itself slows biological processes, which has an interesting side effect. Creatures there often move less, reproduce more slowly, and may exist at lower population densities than similar species in temperate zones. That means encounters are rarer. A species can exist without being easily noticed simply because there are fewer individuals spread across vast areas. Darkness plays a role as well. The polar night lasts months in some regions. No sunlight at all. Under sea ice, even during brighter seasons, light penetration is limited. Visual observation becomes challenging. Cameras need artificial lighting, which can disturb animals or fail to capture subtle details. Some organisms may actively avoid illuminated zones, staying beyond the reach of exploration tools. There's also the issue of ice cover itself. Sea ice shifts, fractures, compresses. Ice shelves carve unpredictably. Leads, those narrow openings in the ice, form and close. An area accessible one week may be sealed the next. Long-term observation stations are difficult to maintain. Instruments can be crushed or carried away. And then there's depth. Parts of the Arctic Ocean exceed 4,000 metres. That's deep anywhere, but combined with cold temperatures and seasonal ice cover, it becomes particularly challenging. Remotely operated vehicles help, but they have limits in battery life, maneuverability, and communication. Autonomous underwater vehicles expand reach, yet retrieval isn't always guaranteed. Biologists often point out something simple, but easy to forget. Every major exploration of previously inaccessible environments has revealed new species. Deep ocean hydrothermal vents, tropical forest canopies, subterranean caves, Antarctic subglacial lakes. The Arctic combines aspects of all those conditions: isolation, temperature extremes, limited light, and difficult access. From a probability standpoint, undiscovered life is expected. Some of that life is likely microscopic. Microbes adapted to cold environments, known as psychrophiles, have been found in sea ice brine channels, permafrost and deep waters. Many remain uncharacterized genetically. Microbial ecosystems can contain enormous diversity, often invisible without advanced sequencing techniques. Entire metabolic strategies may exist there that science has only begun to document. But larger organisms are part of the picture too. Fish species adapted to near-freezing seawater produce antifreeze proteins. Invertebrates inhabit underside ice surfaces, feeding on algae that grow in thin seasonal light. Certain jellyfish, crustaceans, and worms have been observed only a handful of times. Each rare observation hints at broader populations living beyond easy reach. There's an interesting historical pattern. Early Arctic explorers were focused on navigation and survival, not biodiversity. Scientific sampling was secondary. Even in the 20th century, much biological work concentrated near accessible coastlines rather than deep central basins. Only recently have consistent, technologically supported surveys expanded coverage. Climate change complicates the situation. Melting ice opens access, but also alters habitats rapidly. Some species may disappear before being documented. Others may migrate, hybridize, or adapt in ways that obscure clear classification. Scientists sometimes describe it as a race between discovery and environmental change. Indigenous knowledge adds another dimension. Arctic communities have long histories of observation, noticing patterns in animal behavior, migration, and environmental shifts. While not always framed in scientific taxonomy, these observations sometimes hint at organisms or ecological relationships not fully captured in academic literature. Integrating that knowledge carefully is an ongoing process. Acoustics offer another clue. Hydrophones placed under ice occasionally record sounds not yet linked definitively to known species. Biological acoustics is complex, and unidentified signals don't automatically mean unknown animals, but they do encourage further investigation. Sound travels efficiently in cold water, sometimes revealing presence without visual confirmation. Sampling methods themselves can limit discovery. Nets capture certain sizes of organisms but miss others. Sediment cores reveal microscopic life but not mobile species. Environmental DNA sampling, where scientists analyze genetic traces left in water, has started to indicate species presence without direct observation. Sometimes sequences appear that don't match any known database entry. That doesn't necessarily mean entirely unknown large animals, but it does confirm gaps in catalogued biodiversity. Genetic evidence can precede visual confirmation by years. It's a bit like finding footprints without seeing the walker, except at a molecular level. There's also behavioural concealment. Many Arctic animals rely on camouflage, slow movement, or seasonal migration. Some may inhabit narrow ecological niches, such as under ice cavities or deep sediment layers. Those microhabitats are easy to overlook unless specifically targeted. Equipment development continues to improve exploration. Ice-tethered observatories drift with sea ice, collecting long-term data. Autonomous gliders sample water columns quietly. Improved satellite coverage tracks ice dynamics to guide expeditions. Yet even with these advances, coverage remains partial. Another consideration is funding and prioritization. Polar research competes with many global scientific priorities. Expeditions are expensive, safety requirements are high, long preparation times reduce flexibility. That naturally limits how frequently comprehensive biological surveys occur. Despite those constraints, every expedition tends to add something new, sometimes a single specimen, sometimes a previously unrecognized ecological interaction, occasionally a species entirely new to science. The cumulative effect suggests that the Arctic inventory remains incomplete. The public perception often imagines discovery as dramatic, a large animal suddenly revealed. In reality, most biological discovery is gradual. A new species of amphipod here, a microbial lineage there, an unusual fish recorded once and then again years later. Over time, patterns emerge. It's also worth noting that unseen doesn't always mean rare. Some organisms may be abundant but simply located in places difficult to access consistently. Deep pelagic zones, under ice layers, or remote basins could host stable populations largely out of observational reach. Temperature stability under ice can actually create relatively consistent environments compared to surface zones. That stability may support specialized ecosystems that don't fluctuate dramatically season to season, yet remain hidden. As exploration continues, collaboration increases. Oceanographers, biologists, climate scientists, engineers, and local communities contribute different perspectives. That multidisciplinary approach tends to accelerate understanding, though the Arctic still resists quick answers. And as we continue moving through this quiet northern landscape in thought, it helps to keep one simple idea in mind. Unknown life isn't an anomaly. It's the default condition wherever observation is incomplete. The Arctic simply represents one of the last large regions on Earth where that incompleteness remains substantial, which leads naturally into considering why, even today, with satellites overhead and advanced research vessels available, the Arctic remains one of the least directly observed biological regions on the planet, and how those persistent gaps continue shaping what scientists expect to find next. One of the reasons the Arctic continues to resist full biological understanding comes down to something very practical. Distance. Not just distance in kilometres, but operational distance from infrastructure, emergency support, and stable observation platforms. Most ecosystems closer to populated regions have decades or even centuries of accumulated study behind them. The Arctic, by contrast, still involves long travel times, specialised vessels, and environmental uncertainty that makes consistent observation difficult. Research stations exist, of course, scattered across northern Canada, Greenland, Svalbard, Alaska, and parts of Russia. They provide valuable long-term data on climate, ice conditions, and certain wildlife populations. But those stations represent tiny points within an enormous region. The Arctic Ocean alone covers more than 14 million square kilometres. Sampling even a small fraction thoroughly would require sustained effort over many years, and weather windows rarely cooperate with neat research schedules. Seasonality complicates everything further. During winter months, temperatures can drop well below -40 degrees Celsius in some areas. Equipment reliability decreases sharply in those conditions. Plastics become brittle, lubricants thicken, batteries lose efficiency. Even routine outdoor tasks demand protective gear that slows movement and reduces dexterity. Collecting biological samples while wearing thick gloves and face protection becomes an exercise in patience. Darkness during the polar night is another factor that reduces observational capacity. Satellite imaging still functions, but optical systems lose effectiveness without sunlight. Artificial illumination from research vessels can help locally, yet it only covers small zones and can alter animal behaviour. Some species retreat from bright light, while others approach it unpredictably. Either response can skew data. Sea ice dynamics add a layer of unpredictability that few other environments match. Ice is not static. It drifts under the influence of currents and wind, sometimes carrying instruments far from their deployment sites. Pressure ridges form where sheets collide, creating thick barriers. Leads open suddenly, exposing water where ice existed hours before. A planned research transect can become inaccessible simply because the ice rearranged itself overnight. For underwater work, ice cover restricts vessel positioning. Standard oceanographic techniques often rely on free navigation above sampling sites. In heavy ice, ships may need to maintain safe distance from unstable flows, or avoid regions entirely. Autonomous underwater vehicles extend reach, but communication through thick ice remains technically challenging. Data retrieval may be delayed until instruments surface, assuming recovery succeeds. Financial considerations also shape how frequently the Arctic gets studied. Polar expeditions involve icebreaker ships, specialized crews, emergency preparedness systems, and logistical planning that can span years. That level of investment limits the number of missions possible annually. Many proposals compete for limited funding, so biological surveys sometimes share ship time with climate monitoring or geological studies rather than receiving dedicated expeditions. Human safety is always part of the equation. Extreme cold affects not only equipment but also physiology. Frostbite risks increase quickly. Visibility can drop during snowstorms. Ice stability is never fully guaranteed. Field teams undergo extensive training, yet caution naturally limits how far and how often researchers venture into certain zones. Even when access is possible, observation methods introduce bias. Nets and trawls capture organisms within specific size ranges. Cameras capture only what passes within their field of view. Acoustic monitoring identifies movement and sound, but not always species identity. Environmental DNA sampling detects genetic traces, but cannot yet describe full organismal behavior or abundance accurately. Each method contributes partial information. The Arctic Ocean's vertical structure adds complexity. Cold, relatively fresh surface layers sit above deeper, saltier water masses. Those layers influence nutrient distribution, oxygen availability, and light penetration. Biological communities may cluster within narrow depth bands that are easy to miss without precise sampling strategies. A few meters difference in sampling depth can yield very different species compositions. Ice itself hosts ecosystems that remain underdocumented. Brine channels within sea ice contain microscopic life forms, adapted to fluctuating salinity and temperature. These organisms form the base of localized food webs that larger animals exploit seasonally. Studying them requires careful extraction of intact ice cores, followed by laboratory analysis that preserves fragile biological structures. Permafrost adds another hidden dimension. Frozen soils across Arctic land masses contain microbial communities preserved for thousands of years. Some remain metabolically active at very low temperatures. Others enter dormant states. Thawing permafrost releases both ancient microbes and nutrients that reshape contemporary ecosystems. Documenting those transitions takes time and consistent sampling across large areas. Another reason the Arctic remains less observed involves historical research priorities. For much of modern scientific history, temperate and tropical regions received greater attention because of accessibility and biodiversity richness visible at the surface. Polar research gained prominence later, often driven initially by geopolitical interests, navigation routes, or climate science, rather than detailed biological cataloguing. Technological progress is gradually improving the situation. Satellite remote sensing tracks ice thickness, temperature, and primary productivity indicators. Autonomous floats measure salinity, oxygen, and nutrient levels beneath ice cover. Machine learning assists in analyzing acoustic recordings and environmental DNA datasets. These tools expand indirect observation even when direct sampling remains limited. Still, indirect observation cannot replace specimen collection entirely. Taxonomy often requires morphological examination, genetic sequencing, and ecological context. Without physical samples, classification remains tentative. That's one reason new species descriptions from polar regions often follow years after initial detection signals. Climate variability introduces additional uncertainty. Ice extent fluctuates annually. Storm patterns shift. Ocean circulation changes subtly but persistently. Long-term ecological monitoring requires consistency, yet the environment itself is evolving. Distinguishing natural variability from long-term change requires data spanning decades, which only recently began accumulating comprehensively. Noise pollution is emerging as another observational complication. Increased shipping through newly accessible Arctic routes introduces acoustic disturbance. Marine mammals rely heavily on sound for navigation and communication. Altered acoustic environments may change behaviour patterns, affecting where animals appear during surveys. That complicates interpretation of presence or absence data. Political boundaries also influence research access. Arctic territories fall under multiple national jurisdictions. International collaboration exists, but permitting processes, logistical coordination, and diplomatic considerations can slow expedition planning. Scientific goals must align with regulatory frameworks, which vary regionally. Data sharing has improved in recent years, yet legacy datasets remain fragmented. Older records may use incompatible formats or incomplete metadata. Integrating historical observations with modern digital systems requires careful curation. Until that work progresses fully, comprehensive baseline understanding remains incomplete. Public perception sometimes imagines the Arctic as pristine and unchanged, but industrial activity has increased. Resource exploration, fishing, tourism, and shipping all introduce variables affecting ecosystems. Those influences must be accounted for when interpreting biological observations, further complicating research design. Education and workforce development also matter. Polar research requires specialized training in cold weather operations, ice navigation, and safety protocols. Developing that expertise takes time. Expanding the pool of trained researchers supports more consistent observation, but training pipelines remain relatively small compared to other scientific fields. One often overlooked aspect involves simple human endurance. Extended polar missions involve isolation, disrupted circadian rhythms, limited communication, and psychological stress. Maintaining effective research performance under those conditions requires careful planning and support systems. Those factors influence expedition duration and frequency. Despite all these constraints, incremental progress continues steadily. Each expedition refines maps of biological distribution. Genetic databases expand. Instrument reliability improves. Collaboration networks strengthen. The pace may seem slow compared to other regions, but it reflects the environment's demands rather than lack of interest. There's also a philosophical dimension that sometimes appears in scientific discussions. Exploration tends to move outward from centres of population and infrastructure. The Arctic represents one of the last major frontiers, not because it lacks importance, but because it requires sustained commitment to operate safely and effectively there. When scientists compare known species counts across regions, polar areas consistently show higher proportions of recently described organisms relative to total documented biodiversity. That statistical pattern supports the idea that significant discovery potential remains. At the same time, caution remains essential. Expectations of dramatic, undiscovered large animals rarely align with empirical evidence. Most likely undiscovered organisms are small fish, invertebrates or microbial species adapted to specific niches. Their ecological importance can be substantial, even without dramatic visibility. Long-term monitoring programs are beginning to fill observational gaps. Ice-tethered profilers collect year-round oceanographic data. Passive acoustic arrays monitor marine mammal presence continuously. Automated weather and ecological stations transmit data via satellite. These systems reduce dependence on seasonal expeditions. Still, technology cannot fully replace human observation. Interpretation requires context, experience, and sometimes simple presence in the environment. Field notes, visual impressions, and situational awareness often guide future research directions in ways automated systems cannot anticipate. The Arctic's relative invisibility also influences public awareness. Tropical rainforests or coral reefs capture imagination more readily because images are vibrant and accessible. Polar ecosystems appear visually minimal to casual observers, even though biological complexity exists beneath the surface. That perception affects funding priorities and media coverage. Scientific communication is gradually addressing that imbalance, emphasizing the Arctic's ecological significance. Polar regions influence global climate, ocean circulation, and atmospheric chemistry. Understanding their biodiversity contributes to broader planetary models. As observation expands, ethical considerations arise. Increased access can disturb fragile habitats. Research protocols increasingly emphasize minimal impact, careful waste management, and collaboration with local communities. Balancing discovery with preservation remains an ongoing discussion. Another factor involves temporal scale. Arctic ecosystems often operate on slower biological timelines. Growth rates, reproductive cycles, and ecological succession may extend over longer periods than in warmer climates. Detecting trends therefore requires patience and sustained observation. Archival studies sometimes reveal overlooked data. Specimens collected decades ago, stored in museum collections, undergo reanalysis with modern genetic techniques. Occasionally they represent species not previously recognized as distinct. That retrospective discovery adds another layer to understanding. All these elements combine to keep the Arctic among Earth's least fully observed biological regions. Not empty, not unknowable, but still holding substantial gaps in direct human observation. Those gaps create both scientific challenge and opportunity. And as exploration methods continue evolving, attention naturally shifts toward what might exist beneath persistent sea ice layers, especially in deeper zones where light rarely reaches, and where conditions favour specialised life adapted to cold, pressure, and extended darkness, environments that remain among the most difficult on the planet to observe consistently. Ice itself shapes nearly every aspect of Arctic biology, and not just in the obvious way of lowering temperature. It acts as a physical barrier, a light filter, a moving platform, and sometimes a sealed lid over entire ecosystems. The presence, thickness, and seasonal behaviour of sea ice influence which organisms survive, where they live, and how easily humans can observe them. When scientists talk about the Arctic still hiding unseen life, ice is usually the first factor they mention, because it limits access in ways few other environments do. Sea ice is not a uniform sheet. It forms, breaks, drifts, compresses, melts, and refreezes constantly. Some ice lasts only a single season. Other sections persist for years, thickening through repeated freeze cycles. Multi-year ice can reach several meters in thickness, with ridges extending even deeper below the surface. Those structures complicate navigation and also create sheltered microhabitats underneath, where organisms can live with relatively stable conditions compared to open water. From above, thick ice reduces visibility almost completely. Satellite imagery can detect surface features, but it cannot directly show what lies below. Aircraft surveys face similar limitations. Even when open leads appear, they may close quickly, making repeat observation inconsistent. The logistical challenge alone means many areas are sampled rarely or not at all. Light penetration is another major factor. Sunlight reaching Arctic waters is already limited because of high latitude angles. Add ice cover, plus snow accumulation on top of that ice, and the amount of usable light drops dramatically. Photosynthetic organisms, primarily algae living within, or just beneath the ice, adapt to extremely low light conditions. These algae form the base of certain localized food webs, Because they grow in thin layers attached to ice undersides, they are easy to miss unless sampling is specifically targeted. Darkness during the polar night extends this concealment. For several months each year, large areas receive no sunlight. Biological activity does not stop entirely, but observation becomes far more difficult. Artificial lighting used by research equipment illuminates only small zones. Many animals either avoid illuminated areas or react unpredictably, which complicates behavioural studies. Temperature stability under thick ice creates conditions that are surprisingly consistent compared to open water regions. Surface air temperatures may fluctuate widely, but water just beneath the ice often remains close to the freezing point of seawater. That stability allows specialised species to maintain steady metabolic patterns. These species may not migrate frequently, reducing chances of accidental observation by passing vessels. The ice canopy also dampens wave action. Reduced turbulence changes nutrient mixing and sediment transport. Certain small organisms thrive in these calmer conditions. Others depend on seasonal ice breakup to redistribute nutrients. Because those cycles vary regionally, biological communities differ significantly across the Arctic, even when surface conditions appear similar. For researchers, drilling through ice is a standard method to access underlying water. However, drilling operations are slow and equipment-intensive. Each borehole represents a single sampling point within a vast area. Expanding coverage requires time, fuel, and safe weather conditions. Storms or shifting ice can halt operations quickly. Ice movement introduces another complication. Instruments placed through drilled holes may drift as the ice moves. Long-term monitoring systems sometimes travel hundreds of kilometers over months. While that drift provides valuable data about changing conditions, it also complicates interpretation because the observation point is no longer stationary. Under-ice topography is not smooth. Ice keels, formed where flows collide, extend downward irregularly. These structures create shaded cavities and channels where organisms can congregate. Some fish species use those cavities for shelter from predators. Small invertebrates graze on algae attached to ice surfaces. Observing these communities requires maneuverable underwater vehicles capable of operating in confined spaces. Battery performance remains a technical limitation. Cold temperatures reduce energy efficiency, shortening mission duration for autonomous vehicles. Engineers design insulated battery compartments and heating systems, but those add weight and complexity. Mission planning often involves trade-offs between range, sensor capability and endurance. Communication through ice presents additional obstacles. Radio signals do not penetrate seawater effectively, and acoustic communication has bandwidth limits. Many autonomous vehicles store data on board until retrieval. If recovery fails, data may be lost. That risk discourages deployment in particularly unstable ice conditions. Biological concealment also occurs within the ice itself. Brine channels, microscopic pockets of salty liquid trapped during freezing, host microbial communities adapted to fluctuating salinity and temperature. These microbes influence local chemistry and can serve as food sources for slightly larger organisms. Studying them requires careful ice core extraction, followed by laboratory analysis, because disturbance can alter their environment quickly. Snow cover on ice further reduces light penetration. A thick snow layer can block most incoming sunlight, suppressing algal growth underneath. Seasonal variations in snowfall therefore affect productivity cycles. These changes cascade upward through the food web, influencing distribution of zooplankton, fish, and larger predators. Predator-prey interactions under ice remain difficult to document directly. Seals, for example, maintain breathing holes in ice, while polar bears hunt near those openings. Beneath the surface, fish and invertebrates interact in ways still not fully characterized. Acoustic monitoring provides indirect evidence, but visual confirmation remains limited. Climate variability is altering ice patterns, but not uniformly. Some regions experience thinning ice and longer open water seasons. Others maintain thick multi-year ice. That patchwork creates shifting habitats. Species adapted to stable ice may decline locally, while others expand. Tracking those changes requires repeated surveys across large areas, which takes time. Ice also acts as a transport mechanism. Organisms embedded in or attached to drifting ice can travel long distances. When ice melts, those organisms enter new environments. This process influences species distribution and genetic exchange. It can also introduce unfamiliar species into ecosystems where they were previously absent. Human observation from ships is constrained by icebreaker capability. Even the most powerful icebreakers have limits. Fuel consumption increases significantly in heavy ice, reducing time available for research operations. Safety considerations sometimes require maintaining distance from particularly dense ice fields. Sound propagation under ice differs from open water conditions. The ice layer reflects acoustic signals, sometimes enhancing long-distance transmission, but also creating complex echo patterns. Marine mammals use sound extensively, yet interpreting acoustic recordings requires careful calibration to distinguish biological signals from ice movement or mechanical noise. Long-term ecological stations anchored to the seabed provide valuable data, but installation beneath ice cover is technically demanding. Retrieval months or years later involves locating precise positions despite drift and environmental change. Each successful recovery adds data points, but gaps remain between deployments. Another factor influencing hidden biodiversity is simply the scale of the Arctic basin. Even with modern technology, comprehensive coverage is unrealistic in the short term. Scientists prioritize representative sampling areas, but unstudied regions remain extensive. Probability alone suggests undiscovered organisms persist within those zones. Ice edges, where open water meets ice cover, often support higher biological productivity due to nutrient mixing and light availability. These regions attract diverse species but also change position seasonally. Studying moving ecological boundaries requires flexible expedition planning and adaptive sampling strategies. The presence of ice influences oxygen exchange between ocean and atmosphere. Reduced mixing can create localized oxygen gradients that favor specific organisms adapted to lower oxygen conditions. Such specialized niches are easily overlooked without targeted chemical measurements. Thermal layering beneath ice sometimes traps nutrients at certain depths. Phytoplankton blooms may occur briefly when light conditions improve. Those short-lived events can support bursts of biological activity that are easy to miss unless sampling coincides precisely with timing. Ice-associated amphipods, small crustaceans living directly beneath sea ice, illustrate how specialized some Arctic organisms are. They feed on ice algae and detritus, serving as prey for fish, birds, and mammals. Despite their ecological importance, distribution data remains incomplete because sampling requires close proximity to unstable ice undersides. Technological improvements continue to expand observation capacity. Under-ice drones equipped with upward-looking sonar map ice thickness, while simultaneously recording biological data. Improved low-light cameras capture clearer imagery. Genetic sequencing from environmental samples identifies organisms without direct capture, yet each advancement reveals further complexity rather than closing the book. Data integration presents its own challenge. Physical oceanography, climatology, microbiology, and marine ecology all contribute pieces of the puzzle. Coordinating data sets across disciplines takes time. Interpretation often requires iterative analysis rather than immediate conclusions. Another practical limitation involves seasonal research schedules. Many expeditions occur during late spring or summer when conditions are relatively safer. Winter data remains scarcer despite its ecological importance. Year-round autonomous systems help fill gaps, but they cannot capture everything. Ice thickness also affects primary production. Thin seasonal ice allows more light penetration than thick multi-year ice. Regions transitioning between these states may experience shifts in species composition. Monitoring those transitions requires consistent temporal coverage. Because ice limits direct human access, much Arctic biological knowledge still comes from indirect indicators, chemical signatures, genetic traces, acoustic recordings, and sporadic visual encounters form a mosaic rather than a complete picture. That mosaic continues expanding slowly. Researchers often emphasize patience. Discovery in polar regions rarely happens quickly. Instruments fail, weather delays occur, data analysis takes months. Incremental accumulation eventually clarifies patterns. That gradual process explains why the Arctic still holds unseen life despite sustained scientific attention. The concealment effect of ice, combined with extreme climate and extended darkness, keeps portions of the Arctic effectively out of sight. Not permanently hidden, but observed intermittently. Each new observation adjusts understanding slightly, without fully resolving the larger picture. As attention moves deeper beneath persistent ice layers, especially into colder and darker water columns, interest increasingly focuses on how organisms survive where sunlight barely reaches at all. Environments that introduce another level of complexity in understanding Arctic biodiversity. Once you move beneath the shifting lid of Arctic sea ice and descend past the upper cold surface layers, the Arctic Ocean begins to resemble a different kind of world entirely. Light fades quickly, not gradually in the way it does along temperate coasts, but sharply, especially where thick ice blocks most sunlight from entering at all. In some regions, even midday in summer provides only dim, filtered illumination below the ice. A few dozen meters deeper, natural light becomes minimal. Continue downward, and it disappears altogether. The result is an environment where visual observation becomes extremely limited, both for the organisms living there and for the humans trying to study them. This darkness is one of the main reasons the deep Arctic Ocean still holds biological uncertainty. Humans historically explore visually. We rely on sight to identify, classify, and understand organisms. Cameras and lighting help, but they introduce artificial conditions. Many deep-sea species respond to sudden light exposure by retreating, freezing, or altering behavior. That means recorded observations may not fully reflect natural activity. The depth itself is substantial. Large parts of the Arctic basin exceed 3 to 4 kilometers in depth. Pressure increases rapidly with depth, reaching hundreds of times surface atmospheric pressure. Equipment must withstand those forces reliably. Even minor structural weaknesses can lead to equipment failure. Building robust deep-sea vehicles is expensive, which limits how often they can be deployed. Temperature remains close to freezing throughout much of the deep Arctic water column. While this stability helps certain organisms maintain consistent metabolic processes, it complicates instrument operation. Mechanical parts can stiffen. Seals become less flexible. Electronic components require careful thermal management. Research vehicles must balance insulation, energy efficiency, and maneuverability. Another factor influencing limited observation is water clarity combined with low particulate matter. While clear water can allow light to travel further in some oceans, the Arctic's ice cover blocks the initial light source. Without consistent sunlight, photosynthetic activity in deep water is minimal. Most biological productivity relies on organic material drifting downward from surface layers, often seasonally. This downward flux of organic matter, sometimes called marine snow, forms a key food source for deep Arctic organisms. Small particles of algae, detritus, and biological waste sink slowly. Deep-sea invertebrates, bacteria, and fish species feed on these particles. Because the flux varies seasonally with ice melt and phytoplankton blooms, deep ecosystems may experience pulses of activity followed by long, quieter periods. Observing those cycles directly is challenging. Deploying sediment traps and deep cameras helps, but maintaining them over long periods beneath ice requires careful engineering. Retrieval windows are limited. Instruments may drift or become buried in sediment. Each successful recovery provides valuable data, yet coverage remains sparse relative to the ocean's scale. The Arctic Ocean's circulation patterns add complexity. Water masses enter from the Atlantic and Pacific, carrying nutrients, heat, and sometimes organisms. These inflows influence deep ecological conditions subtly. Understanding how these water masses interact requires detailed oceanographic measurements alongside biological sampling. Deep Arctic fish species often show adaptations specific to cold, dark environments. Some possess antifreeze proteins preventing ice crystal formation in tissues. Others have reduced skeletal density or specialized buoyancy mechanisms. Many species remain poorly documented because encounters are infrequent. Occasional trawl samples reveal unfamiliar specimens that require years of analysis before formal description. Invertebrates dominate deep Arctic ecosystems numerically. Polychaete worms, amphipods, brittle stars, sea cucumbers and various crustaceans inhabit sediment surfaces and water columns. Many appear morphologically similar at first glance, yet genetic analysis often reveals distinct species. That hidden diversity contributes to the idea that many organisms remain undescribed. Bioluminescence, the production of light by living organisms, plays a role in deep ocean ecosystems worldwide, including the Arctic. Certain jellyfish, shrimp and fish produce faint light for communication, camouflage, or predation. Observing these displays requires sensitive equipment that does not overwhelm natural signals with artificial illumination. Developing such systems has been gradual. Acoustic methods supplement visual observation. Some fish and marine mammals produce characteristic sounds. Hydrophone arrays record these signals over time. Analysis sometimes identifies patterns not yet matched to known species. While acoustic data alone cannot confirm new organisms, it provides clues about biological presence in otherwise inaccessible zones. Environmental DNA sampling has become particularly valuable in deep Arctic research. Water samples contain trace genetic material shed by organisms through skin cells, waste, or mucus. Sequencing this material can indicate species presence even without direct observation. Occasionally, sequences appear that do not match existing databases, suggesting undocumented biodiversity. However, interpreting environmental DNA requires caution. Genetic material can drift with currents, meaning detection does not always indicate local populations. Researchers combine DNA data with oceanographic modelling to estimate probable organism locations more accurately. Submarine ridges and basins within the Arctic create varied habitats. The Lomonosov Ridge, Alpha Ridge, and other underwater features influence currents and sediment distribution. These structures may support localized ecosystems distinct from surrounding abyssal plains. Detailed mapping continues, but biological surveys lag behind geological understanding. Hydrothermal activity, common in other deep oceans, appears less extensive in the Arctic, but is not absent. Potential vent systems could support specialized chemosynthetic communities, similar to those found elsewhere. Exploration remains limited due to logistical difficulty and uncertainty about vent locations. Sediment composition influences deep-sea life significantly. Fine silts, clay deposits, and organic rich layers host different communities. Sampling cores reveal microfauna diversity that sometimes exceeds expectations. These organisms play roles in nutrient cycling, yet remain largely invisible without microscopic analysis. Seasonal ice melt influences deep ecosystems indirectly. Increased light penetration during summer promotes surface phytoplankton blooms. When these organisms die or are consumed, organic matter sinks, delivering nutrients downward. Variability in ice cover therefore affects deep food availability. Climate trends toward reduced ice cover may increase productivity in some regions, altering deep ecological dynamics. Scientists monitor these changes closely, as shifts in deep biodiversity can indicate broader environmental transitions. Deep Arctic ecosystems also interact with carbon cycling. Organic matter burial in sediments contributes to long-term carbon sequestration. Understanding biological contributions to this process helps refine climate models. Again, limited sampling constrains precision. Exploration technology continues advancing. Remotely operated vehicles now operate longer under ice, equipped with improved navigation systems. Autonomous underwater gliders map large areas quietly. Hybrid systems combine acoustic mapping, imaging and sampling in single missions. Each advancement increases observation reach incrementally. Despite progress, operational risk remains. Recovering deep-sea vehicles under moving ice requires careful timing. Weather changes can delay retrieval. Equipment loss, while infrequent, still occurs. These risks influence expedition planning and insurance considerations. Human presence in deep Arctic research remains episodic. Continuous manned observation is impractical. Most data comes from instruments left in place temporarily or from short-duration dives. That episodic observation leaves gaps in behavioral understanding. Temporal variability adds another layer. Some deep organisms exhibit seasonal reproductive cycles tied to surface productivity. Others reproduce slowly over years. Short observation windows may miss key life stages entirely. Long-term data sets help but remain limited. Collaboration across nations has improved data sharing. Arctic research often involves multinational teams due to cost and scale. Joint expeditions maximize ship time and expertise. Shared databases enhance accessibility, though standardization efforts continue. Public awareness of deep Arctic ecosystems remains relatively low compared to tropical marine environments. Images are less visually dramatic. Media coverage tends to focus on climate change rather than biodiversity. That perception influences funding and educational emphasis. Training new researchers for polar deep-sea work requires specialized programs. Technical skills in cold weather operations, remote vehicle piloting, and interdisciplinary analysis are essential. Expanding that expertise base takes time. Ethical considerations arise as exploration increases. Minimizing disturbance to fragile deep ecosystems is a priority. Sampling protocols emphasize conservation alongside discovery. Balancing knowledge acquisition with environmental stewardship remains central. Scientific curiosity about unseen Arctic life persists, partly because previous deep-sea explorations elsewhere have consistently revealed unexpected organisms. The probability framework suggests similar outcomes in the Arctic, even if discoveries emerge slowly. Each expedition tends to confirm one consistent theme. The deep Arctic Ocean is not barren. It supports functioning ecosystems adapted to darkness, cold, and pressure. Documentation simply lags behind existence. As observation methods improve, attention increasingly shifts toward organisms that live directly beneath persistent sea ice rather than far below it. Communities that combine characteristics of surface and deep ecosystems and remain among the least visually documented anywhere on Earth. Those under ice communities are often closer to the surface than the deep basins just discussed, yet they remain surprisingly difficult to observe directly. The underside of sea ice forms a ceiling over large stretches of the Arctic Ocean, sometimes extending unbroken for hundreds of kilometers. Beneath that ceiling exists a narrow but complex ecological zone where organisms attach, feed, hide, reproduce, and move along the shifting ice boundary. Much of this activity has been inferred from indirect sampling rather than continuous filming, which explains why scientists still expect species there that no camera has clearly captured. The first obstacle is simple positioning. Ships cannot always reach the exact location above a stable ice sheet. Even icebreakers require safe maneuvering space, and pressure ridges can block access. When access is possible, researchers drill holes through the ice to lower instruments. Each hole is labour-intensive to create, and the area it reveals is tiny compared with the surrounding environment. A camera lowered through a single borehole may capture only a few square meters of habitat. Under ice, remotely operated vehicles have improved coverage, but they introduce their own complications. Navigation without GPS requires acoustic positioning systems. Ice keels hanging downward create obstacles. Tether cables risk snagging on uneven ice formations. Autonomous vehicles avoid tethers, but rely on onboard power, limiting operational time. Recovery can be uncertain if the ice shifts before the vehicle resurfaces. Despite these constraints, occasional glimpses have revealed dense biological activity. Amphipods, small shrimp-like crustaceans, often cluster along the ice underside grazing on algae. Some species appear translucent, an adaptation reducing visibility to predators. Others display pigmentation that blends with a dim environment. Genetic analysis suggests several distinct amphipod species remain undescribed because specimens are rare and difficult to collect intact. Ice algae themselves form the foundation of many under-ice ecosystems. These microscopic photosynthetic organisms grow in thin layers where minimal light penetrates. They tolerate fluctuating salinity as ice forms and melts. Seasonal blooms release organic material that feeds zooplankton and fish larvae. Continuous filming of these blooms remains limited, so detailed behavioural interactions among associated species are not fully documented. Fish adapted specifically to under-ice conditions present another area of uncertainty. Arctic cod is one well-known example, frequently associated with ice edges. However, net samples occasionally include small fish that do not match established species descriptions. Some may represent juvenile stages of known species, but others could indicate undocumented diversity. Without repeated visual confirmation, classification remains tentative. Predation patterns beneath ice are still being clarified. Seals hunt fish along ice edges, yet the precise distribution of smaller predators remains unclear. Certain jellyfish species appear intermittently in net samples, suggesting they occupy under-ice zones seasonally. Filming gelatinous organisms is difficult because delicate bodies can be damaged by nets and easily overlooked in low-contrast imagery. Light conditions strongly influence visibility. Even during summer, thick ice combined with snow cover reduces brightness below levels comfortable for standard camera sensors. Researchers employ low-light cameras and specialised illumination, but artificial light can alter natural behaviour. Some organisms freeze in place, others scatter. Achieving a balance between visibility and minimal disturbance requires careful calibration. Temperature stability beneath ice supports slow but steady biological processes. Water just under sea ice typically remains near minus 1.8 degrees Celsius, the freezing point of seawater. Species living there often possess antifreeze proteins or lipid compositions that maintain cell function. Such physiological adaptations are well studied in laboratory settings, but observing how they influence real-world behaviour under natural conditions is still ongoing. Another complication involves seasonal ice melt. As ice thins and fractures, under-ice habitats change rapidly. Organisms attached to ice undersides may detach and drift. Some relocate to newly forming ice elsewhere. This constant restructuring makes long-term filming difficult. A site-productive 1 month may be inaccessible or biologically altered the next. Acoustic monitoring has hinted at biological activity not yet visually confirmed. Hydrophones occasionally record sounds inconsistent with known species signatures. These signals may originate from fish, invertebrates, or even mechanical ice movement interacting with organisms. Distinguishing biological from physical noise requires extensive analysis. Environmental DNA sampling beneath ice has expanded recently. Researchers collect water samples through drilled holes and sequence genetic traces. Some sequences match known Arctic species. Others do not correspond to any reference database entry. That mismatch suggests either undocumented species or insufficient existing genetic data. Follow-up sampling is required to clarify which explanation applies. Invertebrate larvae represent another largely unseen component. Many marine species release planktonic larvae that drift before settling. Under ice larval communities likely differ from open water ones because of temperature and light conditions. Sampling often captures larvae, yet identifying them to species level without adult specimens remains challenging. Ice ridges create miniature caves underneath, spaces shielded from currents and predators. These cavities may host organisms that rarely venture into open water. Navigating such confined spaces with cameras risks damaging equipment, so direct filming is limited. Occasional sonar scans indicate structural complexity greater than previously assumed. Some researchers suspect that certain species time their activity specifically to the polar night, when darkness is complete. Continuous winter observation remains scarce because field operations are riskier then. Autonomous systems help, but interpretation of winter data is ongoing. Behavioural patterns tied to darkness could explain why some organisms remain rarely seen. Microbial mats sometimes form where nutrient concentrations increase locally under ice. These mats support small grazers, which in turn attract slightly larger predators. Visualizing entire food webs in such settings requires simultaneous chemical, biological and imaging data, a technically demanding combination. Under ice currents influence nutrient distribution. Slow circulation can trap organic matter in specific zones, creating localized feeding grounds. Mapping these currents accurately helps predict where organisms might concentrate, yet comprehensive current mapping beneath ice is still incomplete. Climate trends toward thinner ice in some regions may temporarily increase observation opportunities. However, ecological disruption accompanies those changes. Species adapted to thick multi-year ice may decline as seasonal ice dominates. Tracking biodiversity shifts requires sustained monitoring over decades. Human disturbance remains relatively low compared with other oceans, but shipping traffic is increasing in certain Arctic routes. Vessel noise propagates efficiently under ice, potentially affecting animal communication. Monitoring these effects involves both acoustic studies and biological observation. Technological innovation continues gradually. Upward-looking sonar systems map ice undersides while detecting biological targets. Fluorescence imaging highlights organisms invisible in standard lighting. Autonomous docking stations under ice may eventually allow longer vehicle deployments without surface retrieval. Data interpretation benefits from interdisciplinary cooperation. Oceanographers provide physical context. Microbiologists analyze genetic samples, engineers refine instruments, and ecologists synthesize patterns. Each discipline contributes partial understanding that builds toward a fuller picture. Archival footage occasionally yields unexpected discoveries. Cameras deployed for geological or climate studies sometimes capture passing organisms incidentally. Reanalysis of old recordings has identified species not recognized at the time of filming, indicating that hidden biodiversity may already exist within stored data, awaiting careful review. Sampling bias remains an important consideration. Regions easier to access receive more attention, potentially skewing perceived species distribution. Remote Central Arctic areas may harbour communities significantly different from better studied coastal zones. Ice thickness variability influences primary production, which cascades upward through the food web. Thin ice allows more algae growth. Thick ice restricts it. Organisms dependent on algae may migrate accordingly. Observing those migrations directly beneath moving ice remains technically challenging. Predators from above also shape under-ice communities. Polar bears hunting seals create localized disturbances. Seal breathing holes alter ice structure. These interactions indirectly influence smaller organisms below. Quantifying such indirect effects requires integrated observation methods. Temperature anomalies associated with Atlantic water inflow affect certain Arctic regions. Slight warming at intermediate depths may influence species composition beneath ice. Detecting those shifts involves repeated sampling along consistent transects. Educational outreach increasingly highlights under-ice ecosystems, yet visual documentation still lags. Public awareness often focuses on charismatic megafauna like polar bears and whales, while smaller under-ice organisms remain less visible despite ecological importance. Museum collections sometimes contain preserved specimens collected decades ago from under-ice nets. Modern genetic analysis occasionally reveals that these specimens represent distinct species not formally described at the time. Continued re-examination of such collections adds incremental knowledge. Ethical research practices emphasize minimizing disturbance. Excessive drilling, lighting, or netting could harm fragile habitats. Balancing discovery with preservation guides, current expedition protocols, international cooperation helps distribute costs and expertise. Joint Arctic research programs allow broader geographic coverage than single-nation efforts. Data sharing agreements improve cumulative understanding, though harmonizing methodologies remains ongoing. The expectation that unseen organisms exist beneath sea ice rests on consistent patterns from other difficult environments. Whenever access improves, new species tend to be documented. The Arctic follows that pattern gradually rather than dramatically. As observation tools extend range and endurance, attention naturally shifts toward how these under-ice organisms cope with prolonged periods without sunlight, especially during the polar night when biological rhythms adapt in ways that remain only partially documented and continue shaping scientific curiosity about life in persistent darkness. When the sun finally slips below the Arctic horizon for the last time before winter, the change is not dramatic in a single moment. It happens gradually. Days shorten, twilight stretches longer, and eventually the sky stops brightening altogether. Then comes the polar night, a stretch of weeks or months depending on latitude when the sun does not rise at all. For humans, this can feel unusual, sometimes disorienting. For Arctic life, however, it is a regular part of the yearly cycle. Survival during this long darkness is not accidental. It involves biological timing, behavioral adjustment, and physiological strategies that remain only partly documented, because observation during those months is still technically difficult. The first thing to clarify is that darkness does not mean complete inactivity. Many early assumptions suggested Arctic ecosystems would nearly shut down during winter. Research over the last few decades has shown something different. Activity continues, though often in altered patterns. Some species reduce movement to conserve energy. Others shift feeding strategies. Certain predators actually benefit from the darkness, gaining advantage over prey that rely more heavily on vision. Food availability is a major concern during the polar night. Photosynthesis, which depends on sunlight, largely stops beneath thick ice. That means new primary production declines. However, ecosystems rely partly on stored organic matter from the previous summer. Algae blooms during brighter months produce biomass that sinks slowly or remains trapped in ice layers. Many organisms time their feeding to these residual supplies. Zooplankton provide a useful example. These small drifting animals, including copepods and krill, accumulate lipid reserves during productive months. Those reserves act as energy stores that sustain them through winter. Some species enter a state similar to dormancy, slowing metabolism significantly. Others remain active at depth, where conditions are stable and predators fewer. Fish species display varied strategies. Arctic cod, for instance, may remain associated with ice edges even during dark months. Their physiology supports function at near-freezing temperatures. Visual hunting becomes less effective in darkness, so other senses gain importance. Lateral line systems detect water movement. Chemical cues guide feeding. These adaptations allow continued activity even without sunlight. Marine mammals also remain active throughout the polar night. Seals maintain breathing holes in the ice and continue hunting fish. Some whale species migrate out of the region seasonally, while others stay. Acoustic communication becomes especially important in darkness. Sound travels efficiently through cold Arctic water, and many species rely on it for navigation, coordination, and hunting. Observation of these behaviours during polar night remains challenging. Field teams face extreme cold, limited visibility, and safety concerns. Autonomous instruments provide continuous monitoring, but interpretation requires careful analysis. Acoustic recorders, temperature sensors, and low-light cameras contribute pieces of the puzzle rather than complete narratives. Bird life changes dramatically with the onset of darkness. Many species migrate south before winter fully sets in. A few remain, including certain gulls and seabirds adapted to low-light foraging. Their presence depends heavily on open water availability. Leads in the ice provide feeding opportunities, and birds may concentrate around these areas. Terrestrial ecosystems also adjust. Arctic foxes continue hunting through winter, relying on keen hearing to detect prey beneath snow. Caribou reduce movement, conserving energy while foraging on lichens accessible through snow cover. Polar bears maintain hunting patterns tied to seal breathing holes, demonstrating how predator-prey relationships persist even without sunlight. Circadian rhythms, the internal biological clocks that regulate daily cycles, behave differently in polar regions. Without regular light-dark cues, many Arctic animals shift towards seasonal rather than daily rhythms. Hormonal cycles align with long-term environmental changes instead of 24-hour patterns. Research into these adaptations is ongoing and contributes to broader understanding of biological timing. Human circadian systems also respond to polar night. Researchers stationed in Arctic bases often use artificial lighting schedules to maintain stable sleep cycles. Studies on human adaptation provide indirect insights into how other mammals might manage prolonged darkness. Microbial life continues functioning beneath ice and snow. Some bacteria remain metabolically active at very low temperatures, participating in nutrient cycling. Their activity may seem subtle, but collectively it supports ecosystem stability. Because microbes are difficult to observe directly, much understanding comes from chemical measurements and genetic sequencing. The ocean beneath ice retains thermal stability during winter. Surface freezing insulates deeper water from atmospheric extremes. That stability benefits organisms adapted to consistent conditions. While surface air temperatures may drop dramatically, water a few meters below ice remains comparatively stable, allowing continued biological processes. Bioluminescence becomes more noticeable during polar night. Organisms capable of producing light may use it for communication, camouflage, or predation. Observations from deep-sea submersibles and under-ice cameras occasionally capture these displays. However, systematic study remains limited because deploying imaging equipment during winter is technically demanding. Predation dynamics sometimes shift during darkness. Visual predators may lose advantage, while species relying on sound, vibration, or chemical sensing gain relative effectiveness. These changes can alter food web interactions seasonally. Quantifying such shifts requires multi-year data sets. Ice thickness often increases during winter, further restricting light penetration. This reinforces low productivity conditions until spring melt begins. The timing of ice breakup influences when photosynthesis resumes, affecting subsequent biological cycles. Energy conservation strategies appear across many Arctic species. Lower metabolic rates, fat storage, and behavioral changes reduce energy expenditure. These strategies are well documented in terrestrial animals like bears and foxes, but marine species exhibit analogous patterns less easily observed. Long-term monitoring programs have begun capturing winter data more consistently. Ice-tethered profilers measure ocean conditions year-round. Passive acoustic monitoring records animal presence continuously. Satellite observations track ice extent and movement even during darkness. These datasets gradually improve understanding of polar night ecology. Indigenous Arctic communities possess extensive traditional knowledge about winter animal behaviour. Hunting practices historically depended on understanding seasonal patterns. Collaboration between scientists and local communities has enriched ecological interpretation while respecting cultural knowledge. Climate change influences polar night conditions indirectly. Reduced ice extent in some areas increases winter open water, altering heat exchange and ecosystem structure. Such changes may affect species distribution over time. Ongoing observation aims to detect these trends early. Technological improvements in low-light imaging continue expanding observation capability. Cameras sensitive to minimal illumination reduce need for artificial lights. Thermal imaging provides additional insight into animal presence without disturbing natural behavior. Research vessels operating during winter require reinforced safety protocols. Ice navigation, weather unpredictability, and limited daylight demand careful planning. These constraints limit how often winter expeditions occur, contributing to ongoing data gaps. Psychological aspects of prolonged darkness also affect human researchers. Maintaining alertness, mood stability, and operational focus requires structured routines. Support systems at research stations address these challenges, ensuring effective data collection despite environmental stresses. Despite difficulties, winter research yields valuable insights. Discoveries about metabolic adaptation, reproductive timing, and ecosystem resilience emerge gradually. Each dataset contributes to a more accurate picture of how life persists without sunlight. As interest in polar ecosystems grows, winter observation is receiving increased attention. Understanding year-round ecological dynamics is essential for accurate climate modelling and biodiversity assessment. The persistence of life through the polar night demonstrates adaptability rather than dormancy. Activity continues, though often less visibly. Much remains to be documented, particularly among smaller organisms and under-ice communities, and as attention continues moving toward the organisms capable of surviving extreme cold conditions, not just seasonally but continuously, focus increasingly turns to those species classified as extremophiles, organisms that thrive in environmental conditions once thought incompatible with complex life. When scientists first began studying polar environments seriously, there was an assumption that extreme cold would sharply limit biological diversity. The expectation seemed reasonable. Low temperatures slow chemical reactions, reduce metabolic efficiency, and create physical challenges like ice crystal formation in tissues. Yet over time, evidence kept accumulating that not only does life persist in intense cold, it often adapts in ways that allow stable ecosystems to form. The organisms responsible for this are commonly described as extremophiles, species adapted to environmental conditions that would be harmful or lethal to most familiar forms of life. Cold-adapted extremophiles in the Arctic exist across nearly every biological scale. Microorganisms dominate numerically, but multicellular animals, algae, and even certain fungi show remarkable tolerance for sub-zero environments. Their presence is one of the strongest reasons scientists expect additional undiscovered species in the Arctic. Where environmental conditions are difficult to study, specialized life tends to remain partially hidden. One of the most fundamental adaptations involves cellular chemistry. Water normally freezes at 0 degrees Celsius, but seawater freezes closer to minus 1.8 degrees because of salt content. Many Arctic marine organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells. These proteins bind to microscopic ice nuclei, inhibiting growth that would otherwise damage tissues. This biochemical strategy allows fish, invertebrates, and microorganisms to function in water that would freeze unprotected cells. Antifreeze proteins were first studied extensively in Antarctic fish, but similar mechanisms appear in Arctic species. Genetic analysis shows multiple evolutionary pathways leading to antifreeze production. That convergence suggests strong environmental pressure favouring cold tolerance. It also hints that additional undiscovered species may use variations of this adaptation. Membrane fluidity is another key factor. cell membranes must remain flexible enough to allow nutrient transport and waste removal. Cold temperatures tend to stiffen lipid layers. Arctic extremophiles often incorporate higher proportions of unsaturated fatty acids into their membranes, maintaining fluidity even near freezing. This adaptation occurs in bacteria, algae, and higher organisms alike. Metabolic rates in cold environments generally decrease, but not uniformly. Some extremophils exhibit enzymes specifically structured to operate efficiently at low temperatures. These cold-active enzymes catalyze reactions rapidly despite reduced thermal energy. Biotechnology research explores such enzymes for industrial applications, requiring low-temperature processing. Microbial extremophils represent perhaps the least visible yet most abundant cold-adapted life forms. Psychrophilic bacteria and archaea inhabit sea ice brine channels, deep ocean sediments, permafrost soils, and subglacial lakes. Some remain metabolically active at temperatures well below freezing, using dissolved salts or antifreeze compounds to maintain liquid microenvironments. Permafrost microbiology has attracted increasing attention. Frozen soils across Arctic land masses preserve microbial communities for thousands of years. Some organisms enter dormant states, reviving when thawed. Others maintain slow metabolic activity continuously. Genetic sequencing of permafrost samples regularly reveals previously unknown microbial lineages. Cold-adapted fungi also contribute to Arctic ecosystems. They participate in nutrient cycling, decomposition, and symbiotic relationships with plants. Lichens, combinations of fungi and photosynthetic partners, dominate some terrestrial Arctic landscapes. Their slow growth rates and resilience make them important ecological stabilizers. Algae living within sea ice deserve special mention. Ice algae photosynthesize under extremely low light conditions. They tolerate fluctuating salinity as ice forms and melts. Their productivity supports under-ice food webs, providing energy for zooplankton and higher trophic levels. Because these algae grow in thin, often hidden layers, comprehensive documentation remains incomplete. Among multicellular animals, certain nematodes, rotifers and tardigrades demonstrate impressive cold tolerance. Some survive freezing by entering cryptobiotic states where metabolism nearly stops. Water within their tissues stabilizes with protective sugars and proteins. Upon thawing, normal function resumes. These mechanisms continue to be studied for insights into cellular preservation. Arctic fish species display a range of cold adaptations beyond antifreeze proteins. Some reduce metabolic demands by limiting activity. Others develop specialized blood properties, improving oxygen transport at low temperatures. Observing these physiological adaptations in natural settings remains challenging, especially under ice cover. Invertebrates inhabiting Arctic sediments often grow slowly, but live relatively long lives. Sea stars, brittle stars, and certain crustaceans show extended lifespans compared with temperate relatives. Slow metabolism may reduce aging processes, though research continues to clarify these relationships. Extremophiles also adapt behaviorally. Seasonal activity cycles align with temperature fluctuations and food availability. Some species migrate vertically in the water column, seeking optimal temperature layers. Others remain stationary in stable microhabitats. The concept of impossible cold reflects human perception more than biological reality. From a biochemical standpoint, life adapts through incremental evolutionary changes. Environments that appear extreme externally may provide consistent conditions internally. For example, sub-ice waters maintain stable temperatures year-round despite surface weather variability. Laboratory cultivation of cold-adapted organisms presents difficulties. Many extremophils require specific pressure, salinity, or temperature conditions difficult to replicate. As a result, some species are known only from environmental DNA or preserved specimens, rather than living cultures. Environmental DNA sequencing has expanded understanding of Arctic microbial diversity significantly. Water, ice, and sediment samples contain genetic traces indicating organisms not yet isolated physically. Interpreting these signals requires careful analysis to avoid overestimating novelty, yet consistent patterns suggest substantial undocumented diversity. Cold environments influence evolutionary rates differently than warmer regions. Lower metabolic activity may slow mutation accumulation in some species. Conversely, environmental stress can accelerate adaptation in others. Understanding these dynamics helps explain Arctic biodiversity patterns. Extremophile research has implications beyond Earth biology. Astrobiology studies often examine cold-adapted organisms as analogues for potential extraterrestrial life. Icy moons such as Europa and Enceladus present environments where similar biochemical strategies might exist. Arctic research therefore contributes to broader planetary science discussions. Technological advances support extremophile study. Cryogenic sampling techniques preserve delicate organisms during collection. Portable sequencing platforms allow preliminary genetic analysis in field stations. Improved microscopy reveals cellular structures previously difficult to observe. Interdisciplinary collaboration is essential. Microbiologists, oceanographers, geochemists, and ecologists combine expertise to interpret data. Extremophile ecosystems often involve complex interactions among physical conditions, chemical gradients, and biological processes. Climate change introduces uncertainty for cold-adapted species. Rising temperatures may alter habitat stability. Some extremophiles could decline if conditions exceed tolerance thresholds. Others might expand into newly suitable areas. Monitoring these shifts requires sustained observation. Ethical considerations accompany extremophile research. Some environments, such as subglacial lakes, remain largely pristine. Exploration aims to minimize contamination. Sterile drilling protocols and controlled sampling procedures help preserve ecological integrity. Public interest in extremophiles has grown, partly because their adaptations challenge assumptions about life's limits. Educational outreach emphasizes how diverse survival strategies can be. Understanding extremophiles also informs biotechnology, medicine, and environmental science. Data integration remains ongoing. Genetic databases expand continuously, but classification standards evolve. As sequencing technology improves, previously identified organisms may be reclassified. That dynamic process reflects growing knowledge rather than inconsistency. Extremophils remind researchers that absence of evidence does not equal absence of life. Difficult environments often conceal organisms until technology catches up. The Arctic fits this pattern consistently. While microbial extremophils dominate numerically, attention increasingly shifts toward larger, cold-adapted predators operating in dim under-ice environments. These hunters rely less on vision and more on alternative sensory systems, a subject that connects directly with the quieter, less visible predatory dynamics unfolding beneath Arctic waters. As attention gradually shifts from the biochemical resilience of cold-adapted organisms to the animals actively moving through Arctic waters, a different set of survival strategies comes into focus. Predators in the Arctic depths do not rely heavily on sight the way many temperate or tropical species do. Light is scarce for much of the year, and even during brighter months, ice cover filters what little sunlight reaches the water column. Because of that, hunting in these environments often depends on silence, vibration detection, chemical sensing, and extremely subtle movement. Many of these predators remain rarely observed simply because their methods and habitats make them difficult to detect with standard research tools. Sound behaves differently in cold water compared with warmer seas. It often travels farther and with less attenuation, meaning sudden noises can reveal an animal's presence quickly. Predators adapted to these conditions tend to move with minimal disturbance. Slow propulsion, reduced fin motion, and streamlined body shapes limit hydrodynamic noise. These adaptations are not dramatic to the eye. but they become important in environments where acoustic sensitivity determines hunting success. Certain Arctic fish species illustrate this principle clearly. Some deep-dwelling species possess reduced swim bladder structures, minimizing buoyancy adjustments that might otherwise generate noise. Others rely on slow gliding motion instead of rapid fin beats. Because these fish inhabit dim or dark layers, direct filming has been sporadic. Occasional trawl samples confirm their presence, yet sustained visual observation remains rare. Marine mammals also contribute to this quiet, predatory landscape. Some seal species hunt beneath sea ice using breathing holes as access points. Their whiskers, known scientifically as vibrissae, detect minute water movements produced by swimming fish. This tactile sensitivity allows hunting even in near-total darkness. Researchers studying seal whisker mechanics have demonstrated their ability to track hydrodynamic trails long after prey has passed. Certain whales, particularly toothed species that remain in Arctic waters year-round, use echolocation. High-frequency clicks bounce off prey and return detailed acoustic information. While echolocation is not silent in an absolute sense, it is highly directional and often outside the hearing range of many prey species. Recording these signals provides clues about whale presence, but interpreting the data requires careful acoustic analysis. Deep Arctic invertebrate predators are less well known. Some squid and jellyfish species likely occupy these waters, using bioluminescence or stealth approaches. Because gelatinous organisms are fragile, traditional nets often damage them, leaving incomplete specimens. Low-light cameras occasionally capture fleeting images, yet comprehensive behavioural documentation remains limited. Another important sensory adaptation involves chemical detection. Many Arctic predators possess highly sensitive olfactory systems. Dissolved organic molecules released by prey can travel considerable distances in cold water. Fish, crustaceans, and certain worms follow these gradients methodically. Chemical sensing does not produce easily observable behaviour from a distance, which partly explains why some species remain underdocumented. Pressure stability in deep Arctic water allows some predators to adopt ambush strategies. Rather than active pursuit, they remain stationary, conserving energy until prey approaches. Slow metabolism supports this approach. These animals may move infrequently, reducing the likelihood of encounter during short research missions. Acoustic monitoring sometimes reveals biological signals that do not match known species profiles. Short pulse patterns, rhythmic vibrations, or irregular low-frequency sounds appear in data sets. While ice movement and geological processes account for some signals, others remain ambiguous. Scientists approach such data cautiously, avoiding premature conclusions while continuing investigation. The underside of sea ice also hosts predators that remain difficult to film. Certain fish species patrol this boundary layer where small invertebrates gather. Their camouflage blends with dim, uneven light filtering through ice. Upward-looking cameras mounted on autonomous vehicles have captured partial footage, but sustained observation across seasons remains limited. Energy efficiency becomes especially important in cold environments. Predators often favour strategies minimizing caloric expenditure. Slow cruising speeds, infrequent feeding events, and reliance on energy-dense prey help maintain balance. These behaviours produce fewer observable disturbances compared with fast-moving tropical predators. Bioluminescence can play dual roles in predation. Some organisms produce faint light to lure prey. Others use counter-illumination, matching ambient light from above to reduce visibility when viewed from below. In Arctic waters, where ambient light is already minimal, these adaptations may function differently than in lower latitudes. Research continues to clarify these dynamics. Technological limitations still shape observation capacity. Remotely operated vehicles require lighting, propulsion, noise, and tether management. Each factor can influence animal behaviour. Autonomous vehicles reduce noise but have limited operational duration. Passive acoustic arrays record continuously, but lack visual confirmation capability. Seasonal ice thickness influences predator distribution. Thick multi-year ice supports stable under-ice ecosystems, while seasonal ice promotes dynamic edge environments. Predators adapt accordingly, sometimes shifting ranges annually. Tracking such movements requires multi-year data sets that are still accumulating. Environmental DNA has begun revealing traces of predatory species rarely captured physically. Genetic fragments in water samples suggest presence even when animals remain unseen. Combining DNA data with acoustic recordings and occasional visual sightings helps build probabilistic distribution models. Sediment-dwelling predators form another largely hidden group. Certain crustaceans, worms and fish bury themselves partially in seabed sediments, waiting for passing prey. Trawling occasionally collects these organisms, yet direct behavioural observation remains limited due to disturbance caused by sampling methods. Climate variability introduces new complexity. Changing ice patterns alter hunting grounds. Increased shipping noise may interfere with acoustic communication among marine mammals. Shifts in prey distribution cascade through predator populations. Continuous monitoring aims to distinguish short-term fluctuation from long-term trend. Human perception often equates predation with visible pursuit, rapid motion, and dramatic encounters. Arctic predation tends towards subtlety. Silence, patience, and sensory acuity dominate. This difference partly explains why public awareness of these predators remains low, despite their ecological importance. Interdisciplinary collaboration enhances understanding. Engineers develop quieter observation vehicles. Biologists interpret behavioural data. Physicists model acoustic propagation under ice. Each contribution improves the overall picture incrementally. Indigenous Arctic communities have long recognised the quiet efficiency of marine predators. Observational knowledge accumulated through generations informs scientific interpretation, particularly regarding seasonal animal movements and feeding behaviour. Museum collections occasionally yield surprises. Specimens collected decades earlier sometimes represent species not fully recognised at the time. Modern genetic analysis can reveal distinct lineages within what was previously assumed to be a single species. Educational outreach increasingly highlights Arctic acoustic ecology. Public interest in whale communication, for instance, helps support broader research funding. Expanding awareness of less charismatic predators remains an ongoing effort. Ethical research considerations remain central. Minimizing disturbance to animals adapted to quiet environments requires careful protocol design. Reduced engine noise, controlled lighting, and non-invasive sampling techniques receive priority. Data interpretation continues evolving. Machine learning algorithms analyze acoustic datasets more efficiently, identifying patterns humans might miss. Integration with environmental data enhances predictive modeling of predator presence. Despite advances, large portions of Arctic depth remain acoustically monitored rather than visually observed. That distinction matters because behaviour inferred from sound does not always match direct observation. Continued technological refinement aims to bridge this gap. As scientific focus expands from these quiet predators to even smaller, less conspicuous forms of life embedded within ice, sediments, and frozen soils, attention naturally turns toward microbial communities that operate largely unseen, yet influence the entire Arctic ecosystem. As attention shifts from the larger animals moving quietly through Arctic waters to the smallest forms of life, the focus settles on something far less visible but just as important. Much of the Arctic's biological activity happens at a microscopic scale, inside sea ice, locked in frozen soils, or suspended in cold water where human observation rarely reaches directly. These microbial communities do not attract the same attention as whales, fish, or polar bears, yet they shape nutrient cycles, influence climate processes, and support entire food webs. Understanding them is one of the reasons scientists continue to view the Arctic as a region where unseen life almost certainly still exists. Sea ice, which often appears lifeless from above, contains complex internal structures. When seawater freezes, salt does not fit neatly into the ice crystal lattice. Instead, it forms tiny pockets of concentrated brine. These brine channels remain liquid even at temperatures well below the normal freezing point of seawater because the salinity is so high. Within those channels, bacteria, algae and small protists survive and sometimes remain metabolically active throughout the winter. Because the channels are microscopic and fragile, studying them requires careful sampling. Standard drilling or melting procedures can destroy the very structures researchers hope to observe. Ice cores extracted for climate studies often contain microbial communities that were not the primary target of collection. Only later analysis sometimes reveals unexpected biological diversity. Genetic sequencing from these cores frequently produces DNA signatures that do not match existing databases exactly. That does not always indicate entirely new organisms, but it does confirm that microbial cataloguing in polar environments remains incomplete. Permafrost provides another hidden biological reservoir. Unlike seasonal frost, permafrost stays frozen year-round, sometimes for tens of thousands of years. Soil layers trapped in permafrost preserve organic matter, ancient microorganisms, and chemical signatures from past climates. Some microbes enter dormant states and revive when thawed in laboratory conditions. Others appear to maintain extremely slow metabolic activity continuously, functioning at temperatures far below what was once assumed possible. Studying permafrost microbes involves more than biological curiosity. These organisms influence carbon cycling significantly. When permafrost thaws, microbes begin decomposing stored organic matter, releasing carbon dioxide and methane. Those gases contribute to atmospheric warming, which in turn accelerates thaw. Understanding the microbial processes involved helps refine climate predictions. Field sampling of permafrost presents logistical challenges. Remote locations, unstable thawing ground, and extreme weather conditions complicate consistent data collection. Researchers must maintain sterile techniques to avoid contaminating samples, because introducing modern microbes can distort results. Specialized drilling rigs, insulated storage containers, and rapid transport protocols all play roles in preserving sample integrity. Within frozen ground, microbial communities are not evenly distributed. Nutrient availability, soil composition, ice content, and historical environmental conditions create localized niches. Two samples taken meters apart can show very different microbial profiles. That patchiness means broad surveys require many sampling points to build accurate understanding. Subglacial lakes beneath Arctic ice sheets add another dimension. These water bodies remain isolated from the surface for long periods. Limited nutrient input and constant cold temperatures create unusual conditions. Sampling such lakes demands strict contamination prevention, often involving sterilized drilling systems and sealed sampling chambers. Initial studies suggest microbial ecosystems adapted specifically to these isolated environments. Marine sediments beneath Arctic waters host additional microbial diversity. Organic matter settling from the water column accumulates there. Microbes decompose it slowly, participating in nitrogen, sulfur, and carbon cycling. Because sediment layers accumulate over long timescales, they preserve historical biological signals alongside living communities. Core sampling helps reconstruct ecological changes across centuries. Temperature adaptation in Arctic microbes often involves specialized enzymes functioning efficiently at low thermal energy levels. These enzymes maintain reaction rates that would otherwise slow dramatically. Industrial research explores applications such as cold water detergents, food processing, and pharmaceutical production. Studying Arctic microbes therefore has practical implications beyond ecological interest. Salt tolerance is another common adaptation in ice-associated microbes. Brine channels can reach salinity levels several times higher than normal seawater. Organisms surviving there produce compatible solutes, small molecules that balance osmotic pressure without disrupting cellular processes. These biochemical strategies attract attention from biotechnology researchers. Ultraviolet radiation, although limited during winter, can be intense during summer when sunlight reflects off ice surfaces. Some Arctic microbes produce protective pigments or DNA repair mechanisms to handle UV exposure. Observing these adaptations requires both field and laboratory studies because environmental conditions shift seasonally. Dormancy strategies are particularly important. Some microbes reduce metabolic activity to near undetectable levels when conditions worsen. They resume activity when temperature, light, or nutrient availability improves. This flexibility supports long-term survival in fluctuating polar environments. Microbial interactions form complex networks. Bacteria may cooperate metabolically, exchanging nutrients or signaling molecules. Predatory protists feed on bacteria, controlling population dynamics. Viruses infect microbial cells, influencing gene transfer and ecosystem stability. These relationships operate largely unseen yet affect larger ecological patterns. Technological advances in genetic sequencing have expanded knowledge dramatically. Portable sequencing devices now allow preliminary analysis at field stations. Previously, samples required transport to distant laboratories, delaying results. Faster analysis helps guide ongoing sampling strategies during expeditions. Still, genetic data alone cannot reveal full ecological function. Culturing organisms in laboratories remains important, but many Arctic microbes resist cultivation under standard conditions. Replicating precise temperature, pressure, salinity, and nutrient profiles proves challenging. As a result, some organisms remain known only from DNA sequences. Chemical measurements complement biological studies. Researchers analyze dissolved gases, nutrient concentrations, and isotopic signatures to infer microbial activity. For example, methane production in thawing permafrost indicates active microbial metabolism. Linking chemical signals with specific organisms requires careful interdisciplinary work. Remote sensing contributes indirectly. Satellite data tracking temperature, ice extent, and vegetation help identify regions where microbial activity may change. These large-scale observations guide targeted field studies. Long-term monitoring stations provide continuous environmental data. Temperature sensors embedded in permafrost, oceanographic profilers beneath ice, and atmospheric sampling equipment all contribute context for microbial studies. Integrating these data sets improves interpretation accuracy. Human health considerations occasionally arise. Some ancient microbes preserved in permafrost could theoretically include pathogens. Research protocols emphasize containment and safety. However, most identified organisms pose no known risk and instead contribute valuable scientific insight. Public interest in Arctic microbes has grown gradually. Educational outreach often emphasizes their role in climate systems rather than their intrinsic biological complexity. Increasing awareness supports funding and encourages interdisciplinary collaboration. Indigenous knowledge sometimes intersects with microbial research indirectly. Observations of soil stability, water quality, and seasonal environmental changes can guide scientific sampling locations. Collaborative approaches respect traditional expertise while applying modern analytical tools. Data management remains an ongoing task. Large genetic datasets require careful storage, annotation, and accessibility. International collaboration helps standardize methodologies and share findings efficiently. Climate trends toward warming introduce urgency. Thawing permafrost exposes previously frozen microbial ecosystems to new conditions. Some species may expand rapidly, others may decline. Tracking these shifts helps predict ecological consequences. Ethical considerations extend to environmental protection. Minimizing disturbance during sampling helps preserve fragile habitats. Responsible research balances discovery with conservation. Funding priorities influence research pace. Polar microbial studies compete with many global scientific initiatives. Demonstrating relevance to climate modelling, biotechnology, and ecosystem management helps secure support. Interdisciplinary training becomes increasingly important. Researchers combine microbiology, geochemistry, oceanography, and data science skills. This integration improves study design and interpretation. Despite challenges, consistent findings reinforce one conclusion. The Arctic contains extensive microbial diversity still being documented. Each new sampling effort adds data without exhausting discovery potential. As understanding of these microscopic communities grows, attention gradually expands toward how they interact with larger organisms and physical processes, including how microbial activity influences nutrient availability that supports more visible Arctic life forms continuing the ecological chain above them. As researchers continue piecing together how microscopic Arctic communities support broader ecosystems, attention naturally expands toward another aspect of polar biology that receives less casual discussion but carries significant scientific interest. Some Arctic species belong to evolutionary lineages that predate recorded human history by vast margins. Not simply old individuals, but entire genetic branches that have persisted through ice ages, climate shifts, and geological changes while maintaining recognizable biological continuity. These organisms are not unchanged relics in a strict sense, because evolution never fully stops, yet their core biological traits have remained stable enough that scientists describe them as ancient lineages. Cold environments often slow biological processes, including growth, reproduction, and sometimes evolutionary turnover. That does not mean evolution halts, but selective pressures can favour stability when environmental conditions remain relatively consistent over long periods. The Arctic, despite seasonal variation, has maintained prolonged cold phases over geological timescales. Certain species adapted early to these conditions and continued functioning successfully without drastic evolutionary redesign. Marine invertebrates provide clear examples. Some Arctic sponge species show genetic continuity suggesting ancestry extending millions of years. Sponges generally grow slowly, reproduce infrequently compared with smaller organisms, and occupy stable benthic habitats. Deep Arctic waters, with consistent temperature and limited disturbance, allow such organisms to persist over long durations. Occasional sampling reveals individuals that may themselves be centuries old, while their broader lineage extends far deeper into evolutionary time. Arctic bivalves, particularly certain clam species, also demonstrate exceptional longevity. Some individuals have been documented living several hundred years. Their shells preserve growth rings similar to tree rings, allowing researchers to estimate age and environmental conditions during their lifespan. These records provide valuable climate data while illustrating how stable Arctic conditions can support extended biological persistence. Coldwater corals represent another ancient lineage. Unlike tropical reef corals, these species do not rely heavily on photosynthetic symbionts. They inhabit deeper, darker waters where temperatures remain low. Genetic studies suggest some cold-water coral groups originated long before modern human civilizations emerged. Observing them in Arctic regions remains difficult because they often occur at depths requiring specialized equipment. Fish lineages adapted to polar conditions also reveal deep evolutionary roots. Certain nototheniod fishes, while better known in Antarctic waters, have Arctic relatives showing long-term cold adaptation. Their antifreeze protein systems evolved gradually over millions of years. Fossil evidence and genetic analysis indicate continuity through multiple glacial cycles. Crustaceans inhabiting Arctic seabeds frequently display morphological stability across extended periods. Fossil comparisons sometimes show remarkable similarity between ancient specimens and modern relatives. This stability likely reflects successful adaptation to environmental niches, that change slowly compared with more temperate ecosystems. Ancient lineages are not limited to marine environments. Terrestrial Arctic plants include species with evolutionary histories tracing back to earlier glacial periods. Some tundra plants reproduce clonally, meaning new growth emerges from existing root systems rather than seed dispersal. Certain clonal plant colonies may persist for thousands of years, even though individual stems die and regrow. Lichens deserve special mention. These symbiotic partnerships between fungi and photosynthetic organisms colonize harsh Arctic landscapes effectively. Their slow growth rates, combined with environmental resilience, allow persistence across long timescales. Fossil records and genetic studies suggest many lichen lineages have existed far longer than recorded human history. Permafrost soils sometimes preserve biological material from ancient ecosystems. Seeds, pollen, microbes, and small invertebrates trapped in frozen ground provide snapshots of past biodiversity. While not all preserved organisms revive upon thawing, some microorganisms demonstrate viability after extended frozen periods, reinforcing the idea of biological continuity through climatic shifts. Marine sediment cores reveal additional historical biological data. Layers of microscopic shells, organic compounds, and DNA fragments accumulate gradually. Analyzing these layers helps reconstruct species presence across centuries or millennia. Such records show that certain Arctic organisms have maintained stable populations despite environmental fluctuations. Genetic stability in ancient lineages often reflects ecological specialization. Organisms finely tuned to specific temperature ranges, salinity conditions, or nutrient cycles may experience little pressure to change if those parameters remain consistent. The Arctic, though dynamic seasonally, maintains relatively narrow thermal ranges compared with tropical regions. However, stability does not imply stagnation. Subtle genetic drift, localized adaptation, and occasional speciation events occur. Researchers sometimes discover closely related Arctic species differing slightly in morphology or physiology. These differences can reflect microhabitat specialization rather than dramatic evolutionary shifts. Studying ancient lineages requires careful integration of fossil data, molecular genetics, and ecological observation. Fossils provide physical evidence of past forms. Genetic sequencing reveals relationships among living species. Environmental data contextualizes how conditions influence persistence. Combining these approaches produces a clearer evolutionary timeline. Technological advances have improved molecular clock analysis, allowing scientists to estimate divergence times more accurately. By comparing mutation rates across related species, researchers infer when lineages separated. Many Arctic species show divergence dates predating major human cultural developments by wide margins. Cold adaptation itself may promote longevity at both individual and lineage levels. Reduced metabolic rates can lower cellular damage accumulation. While this does not guarantee indefinite survival, it contributes to extended lifespan in some species and potentially slower evolutionary turnover. Environmental isolation also supports lineage persistence. Arctic barriers such as ice cover, extreme cold, and geographic remoteness limit species invasions from warmer regions. Reduced competition allows established organisms to maintain ecological niches without displacement. Climate cycles during the Pleistocene glaciations influenced Arctic biodiversity strongly. Ice sheets advanced and retreated repeatedly. Species capable of surviving cold extremes persisted in refugia or adapted to shifting habitats. Genetic evidence often reflects these historical population movements. Museum collections contribute valuable information. Specimens collected decades ago, sometimes for unrelated studies, provide baseline data for modern comparison. Advances in genetic extraction from preserved samples allow retrospective analysis, extending understanding of lineage continuity. Indigenous Arctic communities have long observed certain species consistently across generations. While traditional knowledge typically focuses on ecological behaviour rather than evolutionary history, continuity of observation reinforces scientific conclusions about species persistence. Ancient lineage research also informs conservation planning. Species with long evolutionary histories may possess unique genetic traits worth preserving. Environmental disruption affecting such species could result in disproportionate biodiversity loss. Climate warming introduces uncertainty. Conditions supporting long-term stability may change faster than some ancient lineages can adapt. Monitoring population trends helps identify vulnerable species early, though predicting exact outcomes remains complex. Ecological roles of ancient species often extend beyond their individual presence. Long-lived organisms such as sponges or corals provide habitat structure supporting diverse communities. Their persistence influences entire ecosystem dynamics. Interdisciplinary collaboration continues to expand understanding. Paleontologists, geneticists, oceanographers, botanists and ecologists contribute complementary expertise. Arctic research increasingly emphasizes integrated data sets rather than isolated studies. Public awareness of ancient Arctic lineages remains limited compared with attention given to more visible wildlife. Educational outreach, highlighting evolutionary continuity, helps contextualize biodiversity conservation within longer historical frameworks. Biotechnology interest occasionally intersects with ancient lineage research. Enzymes from long-adapted cold species may possess useful industrial properties. Ethical sourcing protocols ensure research does not harm fragile populations. Data interpretation requires caution. Apparent stability in fossil records may reflect sampling gaps rather than true absence of change. Continuous refinement of analytical methods improves reliability over time. Despite these complexities, consistent evidence supports the presence of Arctic species whose evolutionary roots extend far beyond recorded human civilization. Their persistence illustrates how life adapts to stable, yet demanding environments over geological timescales. Understanding these lineages also reinforces a broader perspective. Arctic ecosystems are not recent anomalies but long-standing components of Earth's biosphere. Their history predates modern climate science, modern technology, and human exploration of the region. As scientific focus continues expanding, attention naturally turns toward how such long-established species manage visibility and survival in environments where concealment offers clear advantages, leading directly into consideration of camouflage, behavioral subtlety, and other strategies that allow Arctic organisms to remain largely unnoticed, even when present in significant numbers. As research continues revealing how long-established Arctic species persist across millennia, it becomes clear that survival in such demanding environments depends not only on physiology or evolutionary history, but also on behaviour and appearance. Many Arctic organisms remain unnoticed simply because they are very good at avoiding detection. Camouflage, reduced movement, and subtle sensory adaptations all play important roles. These strategies are not dramatic in the way some tropical defensive displays are, yet they are extremely effective in landscapes dominated by ice, low light, and minimal visual contrast. The most obvious example is coloration. Arctic animals frequently display white, pale grey, or translucent body surfaces that blend with snow, ice, or dim water. Polar bears are often cited in discussions of camouflage, but the principle extends across many species. Arctic foxes change coat colour seasonally, shifting from brown or grey in summer to white in winter. This adjustment reduces visibility against snow-covered terrain and improves hunting success while lowering predation risk. Marine species demonstrate similar approaches. Certain fish exhibit silvery reflective scales that mirror ambient light conditions. Under sea ice, where light is diffuse and scattered, such reflectivity reduces visual contrast. Some invertebrates appear almost transparent, minimizing shadows that might reveal their presence to predators or prey. Camouflage in the Arctic often involves more than colour alone. Texture and shape matter. Ice formations create irregular patterns, ridges, and shadows. Animals with uneven fur, mottled skin, or variable body contours blend more effectively into these backgrounds. Observational photography sometimes struggles to distinguish animals even when they occupy the centre of the frame. Silence complements camouflage in many species. Movement through snow, ice, or cold water generates sound that travels efficiently. Arctic predators frequently move slowly and deliberately to reduce acoustic disturbance. Marine mammals such as seals display streamlined swimming styles that limit turbulence. Fish adapted to cold depths often exhibit reduced fin motion, conserving energy while minimizing detectable noise. The Arctic environment itself reinforces these strategies. Low vegetation on land provides little cover, so blending visually becomes essential. Underwater, reduced light penetration means subtle movements may still produce detectable vibrations. Animals sensitive to these cues evolve accordingly, creating a balance between predator stealth and prey awareness. Sensory compensation plays a major role. When visibility declines, other senses gain importance. Many Arctic mammals possess acute hearing capable of detecting faint sounds through snow or ice. Arctic foxes, for instance, can locate rodents beneath thick snow layers by sound alone. Their characteristic hunting leap often follows extended listening rather than visual tracking. Marine species rely heavily on lateral line systems or whisker-like sensory structures. Seals use vibrissae to detect minute water movements left by swimming fish. These tactile cues persist briefly even after prey passes, allowing effective tracking without direct visual contact. Chemical sensing also contributes. Cold water slows molecular diffusion compared with warmer environments, but scent trails still provide useful information. Fish and invertebrates often follow chemical gradients to locate food or avoid predators. Observing such behaviour directly is difficult, which partly explains why some species remain poorly documented. Behavioural timing enhances concealment. Many Arctic animals restrict activity to periods of lowest visibility. During the polar night, continuous darkness favours predators adapted to non-visual hunting. Even in summer, animals may feed during twilight hours when shadows and diffuse light offer better camouflage. Energy conservation intersects with silence. Moving slowly reduces caloric expenditure in cold environments where energy balance is critical. Reduced movement also lowers detection probability. These dual benefits make low-activity strategies particularly advantageous. Reproductive behaviour sometimes incorporates camouflage. Nesting birds select snow-free patches matching egg coloration. Marine species release larvae in seasons when plankton density provides visual cover. Such timing improves offspring survival, while complicating observation by researchers. Human observation methods influence perceived rarity. Fast-moving vessels, bright lights, and mechanical noise can cause animals to withdraw. Quiet, long-duration observation platforms often reveal species previously thought scarce. This suggests that some Arctic animals remain unseen more because of observation disturbance than true rarity. Technological adaptation attempts to address this issue. Passive acoustic monitoring records animal presence without introducing light. Low-noise underwater vehicles reduce disturbance. Thermal imaging detects heat signatures of terrestrial animals against cold backgrounds, though effectiveness varies with environmental conditions. Camouflage strategies sometimes extend to seasonal body condition. Certain marine mammals accumulate fat layers that not only insulate but alter body shape, reducing hydrodynamic noise during swimming. This subtle effect contributes to efficient, quiet movement. Predator-prey interactions evolve accordingly. Prey species develop heightened sensitivity to vibrational scent cues. Predators refine stealth approaches. This evolutionary feedback loop maintains balance while increasing observational difficulty for scientists. Historical exploration accounts occasionally described Arctic regions as empty or sparsely populated. Modern understanding recognizes that perception often reflected observer limitations rather than actual absence of life. Improved observation tools continue correcting those impressions. Museum specimens sometimes reveal camouflage details not apparent in field observation. Close examination of fur patterns, skin textures, or scale structures provides insight into how visual blending operates. These analyses inform ecological interpretation. Indigenous Arctic knowledge frequently emphasizes subtle environmental cues. Traditional hunting practices rely on recognizing tracks, faint sounds, or small visual irregularities. Collaboration between scientists and local communities enriches understanding of animal concealment strategies. Climate change introduces new variables. Altered snow cover, shifting ice patterns, and changing vegetation affect camouflage effectiveness. Some species already exhibit mismatches between seasonal coat color and environmental background. Monitoring these changes helps assess ecological impacts. Educational outreach increasingly highlights camouflage as an adaptive process rather than a static trait. Public awareness of these subtle strategies supports conservation interest and scientific literacy. Data integration remains ongoing. Combining acoustic, visual, chemical, and genetic evidence produces a more comprehensive picture of Arctic biodiversity. No single method captures all aspects of concealment. Funding priorities influence research scope. Projects focused on charismatic species often receive more attention, while smaller or less visible organisms remain understudied. Broadening research agendas helps address this imbalance. Ethical considerations remain important. Minimizing disturbance during observation protects fragile ecosystems and maintains natural behavior patterns essential for accurate study. Technological innovation continues gradually. Machine learning assists in detecting camouflaged animals in photographic datasets. Improved sensors capture faint acoustic or chemical signals. These tools expand observational capability incrementally. Despite advances, Arctic concealment strategies remain highly effective. Many organisms likely exist in significant numbers, yet remain rarely documented visually. This pattern reinforces the idea that absence of frequent sightings does not imply absence of life. As scientific curiosity continues probing these hidden populations, attention increasingly turns toward indirect evidence such as unusual tracks, unexplained acoustic recordings, and historical reports that hint at organisms not yet formally described, opening discussion about how observational clues accumulate before definitive confirmation emerges. As attention shifts from camouflage and quiet behavior to the traces animals leave behind, the conversation naturally moves toward indirect evidence. In the Arctic, direct observation is often rare, but signs of presence appear in other ways. Tracks in snow, unusual acoustic signals beneath ice, occasional partial sightings, or unexpected genetic traces all contribute to a picture that is sometimes incomplete, but still scientifically meaningful. These clues do not immediately confirm unknown species, yet they often guide research by indicating where closer investigation might be worthwhile. Snow tracks provide one of the oldest forms of Arctic observation. Hunters, explorers, and researchers have long relied on footprints to identify animal presence. Snow preserves impressions clearly under stable conditions, but it also distorts easily. Wind reshapes tracks, melting and refreezing alter edges, and overlapping paths complicate interpretation. Experienced observers can often distinguish species reliably, yet occasional track patterns remain ambiguous. Scientists treat such cases cautiously, documenting them without drawing premature conclusions. Ice surfaces can also preserve movement evidence. Seal breathing holes, for example, leave characteristic marks in surrounding snow. Polar bear hunting activity produces recognizable patterns. However, when tracks appear that do not match known behavior precisely, researchers consider environmental distortion first before suggesting unfamiliar animals. This conservative approach maintains scientific rigor. Acoustic evidence plays an increasingly important role. hydrophones deployed beneath sea ice record a wide range of sounds. Known marine mammals produce identifiable vocalizations, but some recordings contain signals not easily classified. These might originate from rarely observed species, unusual environmental interactions, or equipment artifacts. Detailed analysis often involves comparing frequency, duration, repetition patterns, and geographic distribution. The Arctic acoustic environment itself is complex. Ice cracking, pressure ridge formation, and underwater currents generate sounds that can resemble biological signals superficially. Distinguishing physical from biological noise requires expertise in both oceanography and bioacoustics. Even with careful analysis, some recordings remain uncertain. Occasional visual sightings add another layer. Researchers aboard icebreakers or remote field stations sometimes report fleeting glimpses of animals difficult to identify conclusively. Low light, distance, and brief observation windows limit certainty. Standard scientific practice involves documenting conditions carefully, including location, weather, time, and photographic evidence when possible. Environmental DNA sampling has introduced a modern form of indirect evidence. Water samples sometimes contain genetic material that does not match existing reference sequences precisely. This could indicate undocumented species, insufficient database coverage, or degraded DNA fragments complicating identification. Follow-up sampling helps clarify such findings over time. Historical expedition records occasionally describe animals or behaviours not immediately recognised today. While older accounts require careful evaluation due to observational limitations of the time, some contain details consistent with later confirmed species. Researchers review such records selectively, focusing on verifiable environmental context rather than anecdotal interpretation. Indigenous knowledge contributes valuable observational continuity. Arctic communities have tracked animal behaviour across generations. Reports of unusual sightings are often contextualized within broader ecological understanding rather than isolated claims. Collaborative research increasingly integrates this knowledge respectfully, enhancing scientific interpretation without compromising methodological standards. Unconfirmed sightings also occur in marine contexts. Fishermen or research crews sometimes encounter unfamiliar fish or invertebrates. Specimens may escape capture, or partial remains provide insufficient diagnostic features. These events typically prompt targeted surveys in subsequent expeditions. Technological limitations influence confirmation rates. Cameras operating in low light or beneath ice may capture indistinct imagery. Acoustic equipment records sounds without visual context. Genetic sampling identifies presence without morphology. Each method contributes evidence, but rarely provides complete confirmation independently. Scientific caution remains essential. Extraordinary claims require robust evidence. Most ambiguous observations ultimately resolve as known species observed under unusual conditions, environmental noise, or data interpretation challenges. Nonetheless, ambiguous data still serve a purpose by guiding future research priorities. Statistical modelling sometimes uses indirect evidence to estimate probable species presence. Combining acoustic data, environmental DNA, habitat characteristics, and historical records produces probabilistic maps rather than definitive inventories. These models help allocate research resources efficiently. Climate variability adds complexity. Changing ice patterns alter animal distribution. Species previously rare in certain regions may appear more frequently, creating initial uncertainty until patterns stabilize. Continuous monitoring helps differentiate genuine novelty from shifting ranges. Public interest in mysterious Arctic sightings occasionally outpaces scientific evidence. Responsible communication emphasizes uncertainty without dismissing observation outright. Maintaining this balance supports credibility while encouraging curiosity. Museum collections occasionally resolve historical ambiguities. Specimens collected decades earlier may receive new analysis revealing distinct species status. Advances in genetic sequencing often clarify relationships previously uncertain from morphology alone. Acoustic libraries continue expanding. Cataloguing known species sounds improves classification accuracy. Machine learning assists in detecting patterns within large data sets, though human expertise remains essential for interpretation. Satellite imagery sometimes captures large-scale biological indicators indirectly. For example, plankton blooms visible from space suggest food availability influencing higher trophic levels. Such data provide ecological context rather than direct species identification. Funding priorities influence follow-up investigations. Ambiguous evidence competes with many research demands. Prioritization often reflects ecological significance, feasibility, and broader scientific relevance. Ethical considerations apply even to indirect observation. Avoiding unnecessary disturbance during verification attempts protects fragile ecosystems. Non-invasive methods receive preference whenever possible. Interdisciplinary collaboration strengthens analysis, combining expertise from ecology, acoustics, genetics, oceanography, and climatology reduces interpretive bias. Multiple perspectives increase reliability of conclusions. Educational outreach helps the public understand scientific uncertainty. Emphasizing how evidence accumulates gradually fosters realistic expectations about discovery timelines. Despite cautious interpretation, the consistent appearance of ambiguous tracks, unexplained acoustic signals, and occasional unidentified specimens reinforces a central scientific expectation. The Arctic likely contains species not yet fully documented, though confirmation requires systematic study rather than isolated observations. As research infrastructure improves and exploration technology advances, attention increasingly turns toward how modern tools attempt to overcome environmental barriers, particularly how engineers and scientists design equipment capable of functioning reliably in ice-dominated conditions where observation has historically been limited. As the trail of indirect evidence grows, from unusual acoustic recordings to environmental DNA traces and rare physical sightings, the next logical step always involves improving the tools used to investigate those clues. Modern technology has transformed Arctic exploration, compared with even a few decades ago. Satellites monitor ice movement continuously, underwater drones operate for extended periods, and portable genetic sequencers allow preliminary analysis directly at remote field stations. Yet despite these advances, the Arctic still resists complete observation. Ice, cold, darkness, and sheer distance combine in ways that make exploration consistently slower and more complicated than many people expect. The most obvious challenge remains the ice itself. Sea ice is not simply frozen water sitting quietly on the ocean surface. It drifts, compresses, fractures, thickens, and melts according to wind patterns, ocean currents, and seasonal temperature changes. Multi-year ice can become several meters thick, with ridges extending far deeper below the surface. Even the strongest icebreakers must navigate cautiously, because pressure ridges can damage hulls or trap vessels unexpectedly. That risk alone limits where ships can travel and how long they can remain in specific locations. Icebreakers are engineering achievements designed specifically for polar conditions. Their reinforced hulls, powerful engines, and sloped bows allow them to ride up on ice and break it with weight. However, operating such vessels consumes significant fuel and requires experienced crews. Each expedition involves high logistical costs, which naturally limit frequency and duration. Ship time must often be shared among multiple research teams, meaning biological surveys compete with climate monitoring, geological mapping, and other scientific priorities. Aircraft provide another means of access, yet they bring their own constraints. Arctic weather changes quickly. Fog, snowstorms, and high winds can ground flights without warning. Runway infrastructure is sparse in many regions, requiring careful fuel planning and emergency contingency preparation. Helicopters used for ice surveys or instrument deployment have limited range, further restricting operational flexibility. Underwater exploration faces additional complications. Remotely operated vehicles, often called ROVs, allow scientists to film beneath ice and collect samples without sending divers into dangerous conditions. These vehicles operate through tether cables connected to a surface vessel. Ice keels hanging downward create obstacles that can snag cables. Maneuvering carefully reduces risk but also limits exploration speed and coverage. Autonomous underwater vehicles, known as AUVs, remove the tether constraint by operating independently. They follow pre-programmed routes, collecting data until batteries deplete. Cold temperatures reduce battery efficiency, shortening mission duration compared with temperate waters. Engineers design insulated battery compartments and heating systems, but these solutions increase vehicle weight and complexity. Recovery also remains uncertain because shifting ice can block planned resurfacing locations. Communication underwater is inherently difficult. Radio waves attenuate rapidly in seawater, so acoustic communication becomes the primary option. Acoustic signals travel well in cold water, but offer limited bandwidth compared with radio or fibre optic communication. That means data often remains stored on board vehicles until retrieval, rather than transmitted continuously. If a vehicle cannot be recovered, the data may be lost entirely. Satellite observation has revolutionized large-scale monitoring. Ice extent, thickness estimates, surface temperature, and ocean color data provide valuable context. However, satellites cannot easily see through thick ice or deep water. Biological processes occurring beneath ice remain largely invisible from space. Satellite data guide expedition planning, but do not replace direct observation. Low-light conditions introduce another technological hurdle. Cameras require illumination to capture clear images. Artificial lighting can disturb animals or alter natural behavior. Some species avoid bright light, while others approach it unpredictably. Researchers experiment with low-light sensors and red spectrum illumination less disruptive to marine life, but perfect solutions remain elusive. Extreme cold affects electronics reliability. Battery chemistry changes at low temperatures. Liquid crystal displays become sluggish. Lubricants thicken, increasing mechanical resistance. Protective housings, thermal insulation, and internal heating systems mitigate these effects but add weight and energy consumption. Long-term observation platforms attempt to overcome episodic expedition limitations. Ice-tethered profilers drift with sea ice, collecting oceanographic data year-round. Seafloor observatories record temperature, pressure, chemical composition, and sometimes acoustic signals. Deploying and retrieving these systems beneath moving ice requires careful timing and precise navigation. Data storage and transmission also present challenges. Remote Arctic locations lack stable communication infrastructure. Satellite links provide connectivity but at limited bandwidth and high cost. Large datasets such as high-resolution video or genetic sequencing results may require physical transport on storage media after expeditions conclude. Safety considerations remain central. Human researchers working on ice face risks from weather exposure, unstable surfaces, wildlife encounters, and equipment malfunction. Safety protocols limit how far teams travel from support vessels or stations. These constraints reduce sampling coverage compared with more accessible environments. Polar night further complicates operations. Continuous darkness affects visibility and human circadian rhythms. Artificial lighting supports work but increases logistical complexity. Some winter research continues successfully, yet overall expedition frequency remains lower during these months. Environmental protection requirements add another layer. Arctic ecosystems are fragile. Fuel spills, excessive noise, or physical disturbance can have lasting effects. Research protocols emphasize minimal impact, sometimes limiting sampling intensity. Balancing scientific inquiry with conservation remains an ongoing consideration. Ice thickness variability affects instrument deployment. Drilling through multi-year ice requires heavy equipment. Thin, seasonal ice may not support personnel safely. Determining safe access points involves constant monitoring of ice conditions, often delaying planned operations. Ocean currents beneath ice complicate stationary observation. Instruments anchored through ice holes may drift as ice moves. Seafloor anchors reduce drift but complicate retrieval. Each deployment strategy involves trade-offs between stability, coverage, and recovery probability. Funding remains a persistent constraint. Polar research requires specialized ships, aircraft, equipment, and trained personnel. These costs exceed many other scientific fieldwork budgets. Securing sustained funding depends on demonstrating relevance to climate science, resource management, and global ecological understanding. Interdisciplinary coordination increases complexity further. Oceanographers, biologists, climatologists, engineers, and local communities must coordinate schedules, methodologies, and data sharing. While collaboration improves results, it requires additional planning time. Training specialized personnel also takes years. Operating icebreakers, piloting underwater vehicles, conducting cold weather fieldwork, and analyzing complex data sets require expertise developed gradually. Expanding this workforce is essential but inherently slow. Technological innovation continues steadily. Improved sonar systems map under-ice topography more accurately. Autonomous surface vehicles monitor open leads without crew risk. Machine learning assists in analyzing acoustic and visual data sets. Yet each advancement reveals additional complexity rather than eliminating challenges entirely. Climate change introduces both opportunity and difficulty. Reduced ice extent in some regions increases accessibility temporarily. At the same time, thinning ice becomes less predictable, increasing safety risks. Rapid environmental change also complicates baseline comparisons because ecosystems shift while research methods evolve. Public perception sometimes assumes modern technology eliminates exploration barriers completely. In reality, extreme environments always impose limits. The Arctic combines cold, darkness, distance, and moving ice in ways unmatched elsewhere on Earth. Despite these constraints, exploration continues producing incremental knowledge. New species descriptions, improved climate models, and refined ecological understanding emerge regularly. Progress may appear slow, but cumulative data steadily expand the scientific picture. Ethical considerations accompany technological advancement. Autonomous vehicles, acoustic monitoring, and genetic sampling must avoid excessive ecological disturbance. Responsible design and deployment protocols remain priorities. Data integration across decades becomes increasingly important. Historical expedition records, modern satellite observations, and ongoing field measurements together provide the most reliable long-term perspective. Maintaining consistent methodologies where possible supports meaningful comparison. International cooperation plays a growing role. Arctic research often involves multinational teams sharing ships, expertise, and data. Such collaboration maximizes efficiency while addressing global environmental questions. Education and outreach help sustain interest and funding. Communicating the practical importance of Arctic research, including climate prediction, biodiversity conservation, and resource management, supports continued exploration efforts. The Arctic remains one of the last major regions where technological capability still struggles against environmental conditions regularly. That tension between innovation and natural constraint explains why discovery continues slowly rather than rapidly. As exploration technology advances and environmental conditions evolve simultaneously, attention increasingly turns toward how changing climate patterns may accelerate the race to document unknown species before shifting habitats, alter, or even eliminate them, a concern shaping current research priorities across polar science. As exploration technology slowly improves and scientists continue adapting equipment to function reliably in ice-dominated environments, another factor has begun shaping research priorities more strongly than before. Environmental change in the Arctic is occurring faster than in many other regions of the planet. Ice thickness, seasonal duration, ocean temperature, and permafrost stability are all shifting in measurable ways. For researchers studying biodiversity, this creates a complicated situation. On one hand, thinning ice can make some areas temporarily more accessible. On the other hand, habitats that may contain undiscovered species could be altered before they are fully documented. This has led to what many scientists describe informally as a race, not a dramatic competition, but a gradual effort to record biological diversity while conditions are still relatively stable. Sea ice trends illustrate this clearly. Long-term satellite data show declining summer ice extent in several Arctic regions. Thinner seasonal ice replaces older multi-year ice more frequently. Multi-year ice tends to provide stable habitats for specialized organisms, particularly those living on ice undersides or within brine channels. When this ice diminishes, associated ecosystems may shift or disperse. Researchers therefore prioritize surveys in regions where ice stability is changing most rapidly. Ocean temperature increases, even by small amounts, can influence species distribution. Cold-adapted organisms often occupy narrow thermal ranges. Slight warming may push them deeper, farther north, or into refugia where conditions remain suitable. Conversely, species from slightly warmer waters may expand into Arctic zones. Distinguishing between newly arriving species and previously undetected residents requires careful long-term monitoring. Permafrost thaw represents another major ecological transition. Frozen soils that preserved microbial communities for thousands of years are beginning to thaw in some areas. This releases nutrients and greenhouse gases while altering local ecosystems. Microbial species previously isolated in frozen ground may become active again. Documenting their diversity helps scientists understand both ecological consequences and broader climate feedback mechanisms. Freshwater input from melting glaciers and ice sheets changes ocean salinity locally. Salinity influences water density, circulation patterns, and nutrient availability. Some marine species tolerate only narrow salinity ranges, so distribution shifts may follow. Researchers integrate oceanographic measurements with biological sampling to interpret these changes accurately. Changes in primary productivity also matter. Reduced ice cover allows more sunlight into surface waters during summer months. Increased light can stimulate phytoplankton blooms, which form the base of marine food webs. Higher productivity might support greater biodiversity in some areas, though rapid change can also destabilize existing ecological balances. Migration patterns of marine mammals and fish already show adjustments in certain regions. Some species extend seasonal ranges northward. Others alter timing of movement to align with shifting ice conditions. Observing these trends requires coordinated acoustic monitoring, tagging studies, and satellite tracking. Terrestrial ecosystems respond as well. Vegetation zones gradually shift with temperature changes. Shrubs expand into areas previously dominated by low tundra plants. Herbivores adapt feeding patterns accordingly, which in turn influences predator distribution. Documenting these cascading effects helps clarify how biodiversity evolves under climate pressure. For scientists searching for unknown species, changing conditions present both opportunities and challenges. Newly accessible waters allow sampling where thick ice once prevented entry. However, species adapted to older conditions may decline before comprehensive documentation occurs. That uncertainty motivates sustained survey efforts even when logistical conditions remain difficult. Environmental DNA sampling has become particularly valuable in this context. Genetic traces in water or soil can indicate species presence even when direct observation proves difficult. Repeated sampling over time helps track shifts in biodiversity as conditions change. Expanding genetic reference databases improves identification accuracy. Long-term ecological monitoring stations provide critical baseline data. Temperature sensors, ocean profilers, acoustic recorders, and biological sampling programs create continuous records. Without such baselines, interpreting change becomes speculative. Establishing and maintaining these stations requires sustained funding and international collaboration. Climate modelling increasingly incorporates biological data. Understanding how species respond to environmental change improves prediction accuracy for ecosystem dynamics. These models inform conservation strategies, resource management, and policy decisions affecting Arctic regions. Indigenous communities contribute valuable observational continuity. Generations of experience tracking animal behaviour, ice conditions, and seasonal patterns provide insights often unavailable from short-term scientific studies. Collaborative research respects this knowledge while integrating it with modern analytical methods. Public awareness of Arctic change has grown substantially. Media coverage often focuses on visible effects such as melting ice or wildlife displacement. Less attention goes to microscopic organisms or under-ice ecosystems, yet these components play equally important ecological roles. Educational outreach continues addressing this imbalance. Funding priorities reflect growing recognition of Arctic importance. Climate science, biodiversity conservation, and resource management all intersect in polar research. Securing sustained support allows longer-term studies essential for documenting slow ecological transitions. Technological development responds partly to climate-driven research needs. Improved autonomous vehicles, more efficient energy systems, and advanced sensors expand observational capability while reducing operational risk. These innovations benefit both climate monitoring and biodiversity surveys. Ethical considerations remain central. Increased access to previously isolated regions raises concerns about disturbance, pollution, and habitat disruption. Responsible research emphasizes minimal ecological impact alongside scientific discovery. Data integration challenges persist. Combining satellite observations, field measurements, genetic data, and traditional ecological knowledge requires standardized methodologies and collaborative frameworks. Progress continues gradually as international partnerships strengthen. Museum collections offer historical context. Specimens collected decades earlier provide baseline comparison points. Modern genetic analysis sometimes reveals previously unrecognized species within archived material, illustrating how discovery can occur retrospectively as well as through new fieldwork. Climate change also influences disease ecology. Shifts in temperature and species distribution may affect pathogen dynamics. Monitoring microbial communities helps anticipate potential health implications for wildlife and human populations in Arctic regions. Marine protected areas are expanding in some Arctic jurisdictions. Conservation planning increasingly considers both known biodiversity and potential undiscovered species. Protecting habitats proactively helps safeguard ecological integrity, while research continues. Interdisciplinary training becomes increasingly important. Researchers combine climate science, ecology, genetics, engineering, and data analytics skills. Such integration supports comprehensive understanding of complex environmental change. Despite urgency, scientific caution remains essential. Rapid conclusions without sufficient data risk misinterpretation. Balanced approaches emphasize careful documentation while acknowledging incomplete knowledge. The notion of a race reflects awareness that environmental change may outpace discovery rather than competition among researchers. The goal remains understanding ecosystems accurately enough to inform responsible stewardship. Incremental progress continues. Each expedition adds samples, images, acoustic recordings, and environmental measurements. Over time, these datasets build a clearer picture of Arctic biodiversity under changing conditions. As attention expands beyond environmental change alone, researchers increasingly recognize the importance of long-standing observational traditions held by Arctic indigenous communities, whose accumulated knowledge sometimes includes references to animals or ecological patterns science has only recently begun to investigate systematically. As scientific surveys expand and environmental monitoring accelerates, another source of Arctic ecological knowledge becomes increasingly relevant. Long before modern research vessels, satellites, or underwater drones entered the region, indigenous Arctic communities were already observing animal behaviour, seasonal patterns, and environmental changes across generations. This accumulated experience forms a body of knowledge that does not always follow scientific taxonomy, but often reflects careful, repeated observation of ecosystems. Occasionally, these observations include references to animals or behaviours that have not yet been fully documented within formal scientific literature. It is important to approach this topic carefully. Indigenous knowledge is not folklore in the dismissive sense sometimes implied in older academic writing. It represents lived experience shaped by survival, subsistence practices, and long-term environmental familiarity. At the same time, scientific confirmation requires specific types of evidence, such as physical specimens, genetic data, or repeated verifiable observation. Respectful collaboration acknowledges both perspectives without forcing one framework entirely into the other. Arctic indigenous communities, including Inuit, Sami, Chukchi, Nenets, and others across circumpolar regions, traditionally depended on detailed environmental awareness. Hunting, fishing, travel safety, and seasonal migration all required understanding subtle changes in ice conditions, animal movement, and weather patterns. This observational continuity sometimes spans centuries, providing insight into ecological trends long before formal research programs existed. Reports of unfamiliar or rarely seen animals occasionally appear in oral histories or community observations. These accounts often emphasize behavior rather than classification. For example, a community might describe an animal's seasonal appearance, sound, or habitat preference, without assigning it a specific scientific name. Such information can guide researchers toward areas worth investigating further. Acoustic knowledge is particularly notable. Many Arctic communities are attuned to sounds beneath ice or across frozen landscapes. Differences in ice cracking patterns, animal vocalizations, and environmental noise inform travel decisions and hunting strategies. Some acoustic observations recorded historically later matched scientifically documented species once appropriate recording technology became available. Marine mammal behaviour provides a clear example of productive collaboration. Indigenous hunters often recognise migration timing changes before they appear in formal data sets. Their observations help scientists adjust survey schedules and interpret anomalous results. Similar cooperation occurs in fisheries research, where local experience supplements instrument data. Terrestrial wildlife observations also contribute. Arctic fox distribution, caribou migration shifts, and bird nesting patterns have all been tracked informally by communities for generations. These records provide context for interpreting environmental change. Stories describing unfamiliar creatures occasionally enter discussions about undiscovered species. Scientific researchers treat such accounts cautiously, but not dismissively. Detailed environmental context, consistency across multiple observers, and alignment with ecological plausibility all influence how seriously such reports are considered. Historical precedents exist where indigenous observations preceded scientific recognition. Certain whale migration routes, fish spawning locations, and bird behaviour patterns were documented in community knowledge before appearing in academic literature. These examples encourage ongoing respectful engagement. Language itself carries ecological information. Many Arctic indigenous languages include highly specific terminology for ice types, animal behaviour, and seasonal transitions. Translating these terms into scientific frameworks requires careful interpretation because direct equivalents may not exist. Ethical collaboration has become a central focus in modern Arctic research. Protocols increasingly involve community consultation before fieldwork begins. Shared decision-making about research goals, data use and publication helps ensure mutual benefit and respect. Educational exchanges work in both directions. Scientists share findings about climate trends, biodiversity and technological advances. Communities contribute observational knowledge and contextual understanding. This reciprocal approach improves research quality. Some observations initially classified as unconfirmed sightings later find partial explanation through improved technology. Underwater acoustic recordings, satellite tracking, and genetic sampling sometimes clarify previously ambiguous reports. This process demonstrates how different knowledge systems can complement each other over time. Climate change has intensified collaboration. Communities experiencing environmental shifts firsthand often notice changes earlier than remote sensing detects them. Incorporating these observations strengthens scientific monitoring. Conservation planning benefits as well. Indigenous stewardship practices often emphasize sustainable resource use. Integrating traditional ecological knowledge into management frameworks supports biodiversity protection. Museum collections occasionally include specimens obtained through community cooperation. These specimens sometimes represent rare or poorly documented species. Proper attribution and ethical handling of such materials remain important considerations. Data sovereignty has become a significant topic. Communities increasingly seek control over how knowledge shared during research is stored, interpreted, and disseminated. Respecting these concerns strengthens trust and long-term collaboration. Technological accessibility also matters. Portable recording devices, GPS tools, and environmental sensors allow community-led monitoring programs. Such initiatives expand observational coverage while supporting local capacity building. Scientific training opportunities for Indigenous students are growing. Participation in research programs combines traditional knowledge with modern analytical skills, enhancing interdisciplinary understanding. Public communication about Indigenous knowledge requires careful framing. Avoiding sensationalism while acknowledging valuable observational insight maintains credibility and respect. Cultural context influences how ecological information is expressed. Stories, place names, and seasonal narratives often encode environmental data. Interpreting these elements requires cultural sensitivity alongside scientific expertise. Funding agencies increasingly recognize the importance of collaborative research models. Grant programs sometimes require community partnership components, encouraging sustained engagement rather than short-term consultation. Policy discussions about Arctic development, conservation, and resource management now frequently include Indigenous representation. Ecological knowledge contributes to informed decision-making. Academic publications increasingly cite traditional ecological knowledge alongside scientific data. This integration reflects evolving recognition of multiple valid knowledge sources. Technological advances may eventually clarify some long-standing observational uncertainties. Improved underwater imaging, genetic sequencing, and acoustic analysis expand verification capability. Despite progress, some reported creatures remain scientifically undocumented. This does not necessarily indicate entirely unknown large species. More often, it suggests limited sampling, incomplete observation, or behavioral patterns that reduce encounter probability. Respectful skepticism remains essential. Scientific confirmation requires reproducible evidence. At the same time, dismissing long-term observational experience outright would overlook valuable ecological insight. Interdisciplinary conferences now regularly include sessions on traditional ecological knowledge. These forums facilitate dialogue among researchers, community leaders, and policymakers. Educational outreach increasingly highlights collaborative success stories. Demonstrating how combined knowledge improves conservation outcomes helps sustain public support. The Arctic remains a region where observation, interpretation, and discovery continue evolving together. Indigenous knowledge forms an important part of that process without replacing scientific methodology. As research continues integrating these perspectives, attention naturally turns toward evolutionary processes shaping Arctic species themselves, particularly how geographic isolation, extreme conditions, and long-term environmental stability contribute to unique evolutionary pathways in polar ecosystems. As scientific collaboration expands and more observational perspectives come together, one question continues appearing whenever Arctic biodiversity is discussed. How do species evolve in such isolated, demanding environments? The Arctic is not completely cut off from the rest of the world, but it does impose strong environmental filters. Cold temperatures, seasonal darkness, shifting ice cover, and long geographic distances create conditions where populations can remain separated long enough for gradual evolutionary divergence. This process rarely happens quickly or dramatically. Instead, it tends to unfold quietly over generations, often producing species that appear similar externally, yet differ genetically, behaviourally, or physiologically in ways only detailed study reveals. Isolation in the Arctic takes several forms. Physical distance is one factor. Large expanses of ocean, fragmented coastlines, and scattered island groups limit consistent movement between populations. Sea ice sometimes connects regions temporarily, allowing migration, then later retreats, separating those same populations again. These alternating connection and isolation cycles influence genetic exchange. Temperature stability plays an unexpected role. While seasonal changes are pronounced, overall thermal ranges remain narrow compared with temperate regions. Species adapted to these stable cold conditions may find it difficult to expand into warmer waters. This thermal specialization effectively isolates them even without geographic barriers. Depth stratification in the ocean adds another layer. Different water masses, defined by salinity and temperature, occupy distinct vertical zones. Organisms adapted to one layer may rarely cross into another. Over time, such separation can encourage divergence, particularly among fish and invertebrates inhabiting deep Arctic basins. Glacial history has shaped Arctic biodiversity profoundly. During past ice ages, massive ice sheets advanced across northern continents. Species retreated into refugia, regions where conditions remained survivable. When ice receded, populations expanded outward again, sometimes evolving distinct characteristics during isolation. Genetic studies of Arctic plants, fish, and mammals frequently reveal signatures of these historical movements. Marine species often show subtle divergence linked to current patterns. Atlantic inflow, Pacific inflow, and internal Arctic circulation create semi-isolated water masses. Organisms carried by these currents may establish localized populations. Over many generations, genetic drift and selective pressure lead to differentiation. Behavioral isolation can also occur. Differences in breeding timing, migration routes, or habitat preference reduce interaction among populations. Even when physical barriers are minimal, these behavioral factors maintain separation. Birds nesting in slightly different microhabitats, for example, may rarely interbreed despite geographic proximity. Cold adaptation itself encourages divergence. Producing antifreeze proteins, modifying membrane lipids, and adjusting enzyme function require specific genetic changes. Once these adaptations evolve, returning to warmer environments becomes less advantageous. This specialization reinforces ecological separation. Morphological differences sometimes remain subtle. Two fish species may appear nearly identical externally yet show significant genetic divergence. Molecular techniques such as DNA sequencing increasingly reveal these hidden distinctions. This phenomenon, sometimes called cryptic speciation, appears relatively common in polar environments. Reproductive strategies contribute as well. Some Arctic organisms reproduce slowly, producing fewer offspring with higher survival investment. Slower generation turnover can stabilize genetic traits over time while still allowing gradual divergence. Others rely on larval dispersal influenced by currents, which can either connect or isolate populations depending on circulation patterns. Plant evolution in Arctic regions reflects similar patterns. Tundra vegetation often spreads clonally, meaning new growth emerges from existing root systems. Clonal reproduction reduces genetic mixing, but supports persistence under harsh conditions. Occasional seed-based reproduction introduces variation, allowing gradual divergence across geographic ranges. Permafrost stability historically limited soil microbial mixing. Microbial communities isolated in frozen ground for extended periods evolved independently. Thaw events now reconnect some of these communities, creating opportunities for gene exchange previously absent. Isolation does not always lead to speciation. Sometimes it produces locally adapted populations within a single species. Distinguishing between population variation and full species divergence requires careful genetic, ecological, and morphological analysis. Technological advances have accelerated understanding of these processes. High-throughput genetic sequencing allows comparison across large numbers of individuals and species. Phylogenetic analysis reconstructs evolutionary relationships, revealing divergence timelines. Environmental pressures in the Arctic remain strong but relatively predictable. Seasonal darkness, ice formation, and cold temperatures repeat annually. Predictability can stabilize evolutionary pathways, favoring incremental adaptation rather than rapid change. However, unpredictability also exists. Ice movement, storm patterns, and occasional warm events introduce variability. Species capable of flexible response may maintain broader ecological tolerance, influencing evolutionary trajectories. Marine mammals provide interesting examples. Certain Arctic whale populations show genetic distinctions from related species elsewhere, reflecting historical isolation and specialized ecological roles. Continued monitoring clarifies these relationships gradually. Fish communities in deep Arctic basins demonstrate vertical and horizontal divergence patterns. Depth-related temperature gradients and limited food availability encourage niche specialization. Over time, this leads to distinct lineages adapted to specific environmental layers. Bird migration patterns influence divergence differently. Some Arctic birds travel thousands of kilometers seasonally, maintaining genetic exchange across wide ranges. Others remain more localized, allowing differentiation despite similar habitats. Human activity now interacts with these evolutionary processes. Shipping routes, fisheries, and climate change alter habitat connectivity. Some populations may experience increased mixing, while others face new barriers. Conservation planning increasingly considers evolutionary distinctiveness. Protecting genetically unique populations helps preserve adaptive potential. Arctic biodiversity management therefore integrates genetic data alongside ecological observation. Museum collections provide historical genetic material for comparison. Advances in ancient DNA extraction allow researchers to analyze specimens collected decades or centuries ago. Comparing historical and modern samples reveals evolutionary trends over time. Indigenous ecological knowledge sometimes reflects recognition of population differences long before genetic analysis confirmed them. Observations of behavior, migration timing, or physical variation guide scientific investigation. Educational outreach about Arctic evolution emphasizes gradual change rather than dramatic transformation. This perspective helps align public expectations with scientific evidence. Funding agencies increasingly support long-term genetic monitoring projects. Understanding evolutionary response to environmental change requires extended data sets rather than short-term studies. Ethical considerations include minimizing disturbance to isolated populations. Sampling protocols aim to reduce stress while obtaining necessary data. Data integration remains complex. Combining genetic, ecological, oceanographic, and climatic information requires interdisciplinary expertise. Collaborative research networks facilitate this integration. Climate change introduces new evolutionary pressures. Rapid warming may exceed adaptation rates for some species, while others adjust or expand ranges. Monitoring divergence under changing conditions remains an active research area. Despite ongoing study, Arctic evolution continues producing subtle diversity. Many lineages likely remain undocumented, particularly among microorganisms and small invertebrates. Understanding divergence in isolation reinforces a broader theme. Arctic ecosystems are dynamic, not static. Isolation shapes biodiversity gradually, often invisibly, until careful analysis reveals distinct evolutionary pathways. As interest in these evolutionary processes grows, attention sometimes turns toward more speculative questions about whether large, rarely observed Arctic animals might still exist undetected, a topic that requires careful distinction between scientific plausibility, ecological evidence, and public imagination. As the discussion of evolutionary divergence continues, especially in environments where isolation can produce subtle but meaningful biological differences, attention sometimes drifts toward a more speculative but still scientifically grounded topic. People often wonder whether the Arctic might still host large animals that have not yet been formally documented. Not mythical creatures in a dramatic sense, but species that are rare, elusive, or living in conditions where observation remains incomplete. This possibility is treated cautiously in science, yet it is not dismissed outright, because history shows that previously unknown large animals have occasionally been identified once exploration improved. The clearest starting point is probability rather than imagination. The Arctic is vast, difficult to access consistently, and subject to environmental conditions that limit long-term observation. Large areas remain visited only intermittently. Under such circumstances, the existence of poorly documented or rarely observed large animals becomes plausible, though not necessarily likely in dramatic numbers. Scientific caution emphasizes evidence accumulation rather than speculation. One useful comparison comes from ocean exploration more generally. The deep sea outside polar regions has produced discoveries such as the giant squid being filmed alive only relatively recently despite centuries of maritime activity. Certain whale species were classified scientifically decades after being observed indirectly through acoustic signals or stranded specimens. These examples do not guarantee similar discoveries in the Arctic, but they demonstrate that large marine animals can remain poorly documented when habitats are difficult to access. The Arctic Ocean presents several environmental factors that support cautious openness to rare undocumented species. Depth, cold temperature, seasonal darkness, and persistent ice cover all reduce observation frequency. Research vessels cannot maintain continuous presence across the entire region. Autonomous monitoring helps, but does not cover every ecological niche. Food availability is often cited when discussing large animal feasibility. Large animals require stable energy sources. In the Arctic, primary productivity fluctuates seasonally, yet certain areas support consistent food webs. Ice edge ecosystems, deep basins receiving organic fall from surface blooms, and migratory prey populations could theoretically sustain rare large predators without frequent human observation. Marine mammals illustrate how easily large animals can remain unseen in specific contexts. Some beaked whales, for instance, were classified scientifically only after acoustic studies identified distinct vocal patterns. Visual sightings followed later. In the Arctic, similar acoustic monitoring occasionally records signals not fully matched to known species, though most eventually find conventional explanations. Fish communities in deep, cold waters also remain incompletely catalogued. Large, slow-moving fish adapted to pressure, and darkness could plausibly exist in low densities. Trawl sampling rarely covers every depth consistently, and some fish avoid nets effectively. Advances in environmental DNA sampling occasionally detect genetic traces suggesting species not yet visually confirmed though interpretation requires careful validation. Terrestrial Arctic environments provide less opportunity for undiscovered large animals compared with marine settings, because land areas receive more regular observation through satellite imaging, aerial surveys, and community presence. Nonetheless, rare individuals or small isolated populations of known species occasionally appear outside expected ranges. These cases reflect distribution uncertainty rather than entirely unknown species. Historical exploration records sometimes describe unfamiliar animals. Scientific review of such accounts usually finds conventional explanations such as misidentification, unusual viewing conditions, or environmental distortion. Still, some historical descriptions guided later targeted surveys that confirmed rare species presence. Acoustic monitoring beneath sea ice continues expanding. Continuous hydrophone arrays detect marine mammal vocalizations year-round. Machine learning analysis helps classify patterns. Occasionally, signals remain unidentified temporarily, prompting further investigation. Most ultimately align with known species once additional data accumulates. Satellite tagging programs have improved understanding of animal movement. Tags placed on whales, seals, and large fish reveal migration routes previously unknown. These studies sometimes identify regions where animals spend time unexpectedly, guiding future surveys. Such findings refine ecological maps rather than uncover entirely unknown species. Environmental DNA provides another indirect approach. Water samples collected across Arctic regions sometimes contain genetic sequences not matching reference databases exactly. This could reflect undocumented species, genetic variation within known species, or incomplete database coverage. Continued sequencing gradually reduces uncertainty. The concept of rare undocumented animals often overlaps with cryptic species, organisms visually similar to known species but genetically distinct. Genetic analysis increasingly reveals such cases among fish, invertebrates, and even mammals. These discoveries typically involve subtle differentiation rather than entirely new large animal forms. Behavioral factors contribute to limited observation. Some marine mammals surface briefly, avoid vessels, or inhabit areas with persistent ice cover. Certain fish remain near seabeds where cameras rarely operate. Low-density populations further reduce encounter probability. Climate change introduces additional complexity. Shifting habitats may bring previously isolated populations into new regions. Initial sightings can appear unusual until ecological context becomes clearer. Monitoring these shifts helps distinguish range expansion from undiscovered species presence. Public fascination with large, unknown Arctic animals sometimes reflects broader cultural interest in unexplored environments. Scientific communication emphasizes evidence-based interpretation, while acknowledging that incomplete observation always leaves room for cautious curiosity. Indigenous knowledge occasionally includes references to rarely seen animals or unusual behavior patterns. Collaborative research treats such observations respectfully, while seeking corroborating evidence through scientific methods. In some cases, community observations have preceded formal documentation of species distribution changes. Museum collections occasionally contain specimens initially misclassified or overlooked. Re-examination using modern genetic techniques has clarified species boundaries. While these cases rarely involve large charismatic animals, they demonstrate how discovery can occur retrospectively. Technological advances continue improving detection capability. High-resolution sonar maps seafloor habitats. Autonomous underwater vehicles operate quietly for extended periods. Improved low-light imaging captures clearer footage beneath ice. Each innovation reduces observational gaps incrementally. Energy requirements remain a limiting factor for hypothetical large undiscovered Arctic animals. Stable prey populations, suitable habitat, and reproductive viability must all align. Ecological modelling helps assess whether such conditions plausibly exist. Conservation biology takes a precautionary approach. Even without confirmed undiscovered large species, protecting habitats supports overall biodiversity. Marine protected areas, sustainable fisheries management, and pollution prevention benefit both known and potential unknown organisms. Educational outreach increasingly explains how scientific discovery works gradually. Rare species identification usually follows systematic observation rather than sudden dramatic encounters. This perspective helps manage expectations realistically. Funding considerations influence research priorities. Large-scale expeditions require substantial resources, demonstrating ecological importance, climate relevance, or conservation benefit helps secure support for continued exploration. Interdisciplinary collaboration remains essential. Marine biology, oceanography, acoustics, genetics, and engineering all contribute to detecting elusive animals. Integrated datasets provide the most reliable conclusions. Ethical research practices emphasize minimal disturbance. Avoiding excessive noise, pollution, or habitat disruption protects fragile ecosystems while research proceeds. Despite extensive study, some Arctic regions still receive limited direct observation. Persistent ice cover, deep basins, and remote coastlines maintain conditions where rare species could exist with minimal human encounter. Scientific consensus generally holds that entirely unknown large Arctic animals are possible, but unlikely to be numerous. More probable are rare populations, cryptic species, or organisms adapted to conditions reducing visibility. Continued monitoring remains the practical approach. Acoustic surveys, genetic sampling, visual observation, and community collaboration together build a clearer understanding over time. Incremental discovery is the norm rather than the exception. Each expedition contributes data refining ecological models. Occasionally findings challenge previous assumptions, prompting revised understanding. The Arctic remains one of the few regions where environmental conditions still meaningfully limit observation despite advanced technology. That limitation maintains scientific interest while encouraging careful, evidence-based interpretation. As attention shifts from the possibility of undiscovered large animals toward broader ethical considerations, discussion increasingly focuses on whether every species must be documented, or whether some ecosystems might benefit from remaining relatively undisturbed while research proceeds cautiously alongside conservation priorities. As discussions about rare or possibly undocumented Arctic animals continue, another question gradually moves into focus, and it is less about biology itself and more about responsibility. Scientific curiosity naturally encourages discovery. Researchers want to understand ecosystems, document biodiversity, and reduce uncertainty wherever possible. At the same time, the Arctic remains one of the few regions where human impact, although growing, is still relatively limited compared with many other parts of the world. That creates a thoughtful tension. If exploration becomes easier, should everything be studied as intensively as possible? Or are there situations where restraint serves ecosystems better? Scientific exploration historically aimed to reduce unknowns. Mapping coastlines, cataloguing species, and measuring environmental conditions helped humanity understand how the planet functions. Those goals remain valuable. Accurate knowledge supports climate prediction, conservation planning, and resource management. However, experience from other regions shows that increased access often brings unintended consequences alongside discovery. Disturbance is one of the most immediate concerns. Research vessels generate noise that travels efficiently through cold Arctic waters. Marine mammals rely heavily on sound for navigation and communication. Repeated disturbance could alter migration patterns or feeding behavior. Scientists increasingly design quieter propulsion systems and limit operational duration in sensitive areas to reduce these effects. Physical habitat disruption can also occur during sampling. Trawling for biological specimens disturbs seabed communities. Drilling through sea ice alters microhabitats where algae and microorganisms live. Even careful operations carry some level of impact. Ethical research protocols emphasize minimizing disturbance while still collecting meaningful data. Pollution risk represents another factor. Fuel spills, chemical leaks, or equipment loss in polar environments can have long-lasting consequences because cold temperatures slow natural degradation processes. Strict environmental safeguards now accompany most Arctic expeditions, including redundant containment systems and waste management plans. Climate change already exerts pressure on Arctic ecosystems. Increased exploration adds an additional variable. Researchers therefore weigh the benefits of data collection against potential cumulative effects. Sometimes remote sensing or non-invasive techniques provide sufficient information without direct sampling. The concept of precautionary conservation has gained traction. Protecting habitats before complete species inventories exist can prevent biodiversity loss. Marine protected areas in Arctic waters reflect this approach, establishing conservation zones based on ecological significance, rather than complete species lists recognizes that unknown organisms may depend on those environments. Indigenous perspectives often emphasize stewardship rather than discovery alone. Many Arctic communities traditionally approach environmental interaction with long-term sustainability in mind. Integrating these perspectives into research planning encourages balanced decision-making. Data ownership and benefit sharing also form part of ethical exploration discussions. When research occurs in regions inhabited or traditionally used by indigenous communities, questions arise about how findings are shared, how knowledge is applied, and who benefits from scientific outcomes. Collaborative agreements increasingly address these concerns. Scientific transparency contributes to ethical practice. Publishing methodologies, environmental impact assessments, and research outcomes allows peer evaluation and public accountability. Open data initiatives help ensure findings support broader environmental understanding rather than narrow interests. Technology offers partial solutions. Autonomous vehicles reduce the need for large crews on fragile ice surfaces. Passive acoustic monitoring gathers data without bright lighting or physical disturbance. Environmental DNA sampling identifies species presence through water analysis rather than specimen capture. Each technique reflects efforts to balance discovery with minimal impact. Funding priorities influence ethical considerations. Sponsors sometimes emphasize rapid results or commercial potential. Scientists advocate maintaining ecological responsibility, even when timelines are tight. Peer review and institutional guidelines support this balance. Education plays an important role. Public understanding of ethical exploration encourages support for conservation-oriented research. Communicating why certain areas remain lightly studied can prevent misinterpretation as scientific neglect. Historical experience offers cautionary examples. Regions once considered remote and pristine have experienced rapid ecological change following increased access. Fisheries expansion, tourism, and industrial activity can follow scientific discovery. Awareness of this pattern informs current Arctic policy discussions. Some researchers propose the idea of knowledge thresholds. When sufficient information exists to support conservation decisions, additional intrusive sampling may provide diminishing returns relative to environmental impact. Determining such thresholds requires interdisciplinary judgment. Ethical frameworks also consider future generations. Preserving ecosystems partly unknown today allows future scientists, possibly with less invasive technology, to study them under better conditions. This long-term perspective encourages measured exploration rather than exhaustive immediate documentation. There is also philosophical reflection involved. Human curiosity is a powerful driver of progress, yet it benefits from restraint. Recognizing that some uncertainty may persist without harm challenges the assumption that every unknown must be eliminated quickly. Regulatory structures increasingly reflect ethical exploration principles. Environmental impact assessments, research permitting processes, and international agreements guide Arctic activity. Compliance requires coordination among scientists, governments, and local communities. Monitoring cumulative impact remains essential. Even low-impact individual projects can add up over time. Data sharing among research teams helps track overall environmental pressure. The conversation extends beyond wildlife. Cultural heritage sites, archaeological remains preserved in permafrost, and traditional land use areas also require protection. Ethical exploration respects both ecological and cultural dimensions. Technological optimism sometimes suggests that future tools will eliminate environmental impact entirely. While improvements continue, complete neutrality is unlikely. Awareness of residual impact informs cautious planning. Some scientists advocate observe first, sample later strategies. Extensive remote observation helps identify critical areas before physical intervention. This sequencing reduces unnecessary disturbance. Interdisciplinary ethics committees increasingly evaluate polar research proposals. Including ecologists, social scientists, engineers, and community representatives broadens perspective. Climate urgency complicates ethical decisions. Rapid environmental change means delayed study could result in lost information. Balancing urgency with caution requires nuanced judgment rather than fixed rules. Educational institutions training future polar researchers now incorporate environmental ethics into curricula. Developing awareness early supports responsible long-term practice. Public dialogue about Arctic exploration continues evolving. Media representation influences perception, sometimes emphasizing dramatic discovery while underrepresenting ethical considerations. Balanced communication remains important. Despite complexities, most Arctic researchers share common goals: protect ecosystems, improve understanding, support sustainable management, and collaborate respectfully with local communities. Ethical exploration seeks to align these goals rather than treat them as competing priorities. Gradual progress in non-invasive methods offers optimism. Improved imaging, genetic sampling, and remote sensing reduce the need for disruptive techniques. Continued innovation will likely enhance this trend. Ultimately, the question of whether everything should be discovered does not have a simple yes or no answer. It involves context, environmental sensitivity, technological capability, and societal values. Scientific curiosity continues, but increasingly guided by responsibility. As ethical considerations shape exploration strategies, attention often shifts toward the broader lessons unknown Arctic life offers about Earth systems and even about how scientists think about life beyond this planet, connecting polar research with wider scientific questions. As conversations about ethical exploration continue shaping how scientists approach the Arctic, a broader perspective gradually emerges. Unknown or poorly documented life in polar regions is not only a local curiosity, it contributes to understanding how life functions on Earth as a whole, and, in some cases, how scientists think about the possibility of life in extreme environments beyond our planet. These lessons develop slowly through accumulated research, rather than dramatic single discoveries, yet they influence fields ranging from climate science to microbiology and planetary exploration. One of the clearest lessons involves adaptability. Arctic organisms demonstrate that life persists under conditions once considered too harsh for sustained biological activity. Extreme cold, seasonal darkness, variable salinity, and limited food availability all create challenges. Yet ecosystems function, often steadily. This reinforces a broader biological principle. Environmental limits for life are often wider than are initially assumed. Such understanding helps refine ecological models and informs exploration of other extreme habitats on Earth. Cold-adapted microbial communities particularly expand this perspective. Bacteria and archaea thriving in sea ice brine channels, deep ocean sediments, or permafrost soils show metabolic flexibility that challenges earlier assumptions about minimum temperature thresholds for life. These findings inform climate science because microbial activity influences greenhouse gas cycling, nutrient distribution, and ecosystem stability. Carbon cycling research provides a concrete example. Arctic permafrost contains vast stores of organic carbon accumulated over thousands of years. Microbial decomposition following thaw releases carbon dioxide and methane. Understanding these processes improves climate projections. Without studying microbial diversity and function in polar regions, climate models would remain less accurate. Marine ecosystems beneath Arctic ice also illustrate interconnectedness across global systems. Phytoplankton blooms influenced by ice cover affect carbon sequestration and ocean chemistry. These processes influence atmospheric conditions far beyond the polar region. Documenting biodiversity in these systems therefore contributes to understanding planetary-scale environmental dynamics. Arctic species also demonstrate physiological resilience. Antifreeze proteins, cold-active enzymes, and membrane adaptations illustrate how organisms maintain function under thermal stress. These biological strategies attract attention from biotechnology, medicine, and industrial chemistry. Applications include improved cryopreservation techniques, low-temperature industrial processes, and pharmaceuticals. The study of longevity in cold environments offers additional insight. Some Arctic organisms live significantly longer than related species in warmer climates. Slower metabolism, reduced oxidative stress, and stable environmental conditions may contribute. Research into these mechanisms informs aging studies and cellular biology. Behavioral adaptation provides another lesson. Seasonal cycles in the Arctic are extreme. Continuous daylight in summer transitions to months of darkness in winter. Animals adjust feeding, reproduction, migration, and communication accordingly. These behavioral strategies illustrate how ecosystems respond to environmental variability without collapsing. Food web structure in Arctic ecosystems often appears simpler than in tropical regions, but remains functionally robust. Fewer species may occupy broader ecological roles. Studying such systems helps ecologists understand resilience and vulnerability within ecosystems facing environmental stress. Isolation in polar regions also offers evolutionary insights. Genetic divergence among Arctic populations reflects long-term environmental stability punctuated by periodic change. This pattern helps scientists understand speciation processes in other isolated habitats worldwide. Astrobiology research draws indirect inspiration from Arctic extramuffles. Icy moons such as Europa or Enceladus present conditions involving cold temperatures, limited light, and possible subsurface oceans. Studying how life persists in analogous Earth environments informs hypotheses about extraterrestrial habitability. This does not imply direct similarity but provides useful biological context. Subglacial lake studies reinforce this connection. Microbial communities isolated beneath ice sheets function with minimal external input. Investigating their metabolism helps scientists consider how life might operate in similarly isolated environments elsewhere. Technological innovation often follows scientific curiosity. Instruments designed for Arctic exploration, including low-temperature sensors, autonomous underwater vehicles and remote genetic sequencing tools, find applications in other scientific fields. Polar research thus contributes to broader technological development. Unknown Arctic life also highlights the importance of incomplete knowledge. Scientific humility becomes practical when dealing with vast environments where observation remains limited. Recognizing uncertainty encourages careful interpretation, iterative research, and open collaboration. Education benefits as well. Arctic biology provides compelling examples for teaching ecology, evolution, climate science, and environmental ethics. Demonstrating how organisms adapt to extreme conditions captures interest while illustrating fundamental biological principles. Indigenous knowledge continues contributing to this broader perspective. Observational continuity across generations complements short-term scientific data sets. Integrating these perspectives enriches understanding of environmental change and biodiversity. Conservation strategies increasingly incorporate lessons from Arctic ecosystems. Recognizing how specialized species respond to environmental stress informs global biodiversity management. Protecting fragile habitats before complete species inventories exist reflects this precautionary approach. Data integration remains essential. Combining satellite observations, field sampling, genetic sequencing, and traditional ecological knowledge produces the most comprehensive understanding. Arctic research increasingly emphasizes interdisciplinary collaboration. Public perception of the Arctic often focuses on ice coverage or iconic animals. Expanding awareness of microbial diversity, under-ice ecosystems, and subtle evolutionary processes helps build a more accurate picture of the region's biological significance. Policy discussions about climate change, shipping routes, resource extraction, and conservation rely partly on scientific understanding of Arctic ecosystems. Unknown species and incomplete data highlight the need for cautious decision-making. Research funding agencies recognize the broader implications of polar studies. Supporting Arctic exploration contributes not only to regional knowledge but to global environmental science. Museum collections and historical records continue providing retrospective insight. Reanalysis of older specimens using modern techniques sometimes reveals previously unrecognized biodiversity, illustrating how discovery unfolds over time. Technological improvements will likely continue expanding observational capability. Autonomous vehicles, advanced imaging systems, and portable genetic tools reduce logistical barriers gradually. Yet environmental constraints ensure some uncertainty will persist. Ethical exploration principles discussed earlier remain relevant. Balancing curiosity with responsibility ensures research benefits ecosystems rather than disrupting them unnecessarily. Unknown. Arctic life ultimately reinforces a central scientific understanding. Earth's biosphere is complex, interconnected, and still partially unexplored despite advanced technology. Each new discovery adjusts rather than completes the picture. This perspective naturally leads toward a reflective closing view of the Arctic itself, not as an empty frontier waiting to be filled with knowledge, but as an active, living system where mystery, discovery, conservation, and scientific curiosity continue evolving together without a definitive endpoint. As the broader implications of Arctic life come into view, from microbial resilience to global climate connections and even questions about life beyond Earth, it becomes easier to see the region not as a blank white space on a map, but as a functioning layered system still revealing itself gradually. The Arctic has never truly been empty. It has simply been difficult to observe consistently. Ice, distance, darkness, and environmental extremes have slowed exploration, not prevented life. That distinction matters because it frames the Arctic less as a mystery waiting to be solved completely, and more as an ongoing process of observation and understanding. Scientific exploration rarely ends with a final answer. Each discovery tends to raise additional questions. In the Arctic, this pattern is particularly clear. New species descriptions, improved climate data, and refined ecological models expand knowledge incrementally. At the same time, environmental change reshapes habitats while research continues. The result is a dynamic balance between discovery and adaptation rather than a finish line. The idea of a frontier often suggests conquest or completion. In modern science, especially in fragile environments, the concept has shifted. A frontier now often means an area where learning continues alongside conservation. Researchers increasingly recognize that understanding ecosystems also requires preserving them. Knowledge without stewardship would ultimately reduce the very diversity being studied. The Arctic illustrates this balance clearly. Climate change influences ice extent, ocean temperature, and terrestrial ecosystems. Shipping routes expand in some seasons. Resource exploration remains a topic of policy discussion. These developments bring economic opportunity, but also ecological responsibility. Scientific research provides data supporting informed decision-making, yet it also highlights uncertainties that require caution. Biodiversity documentation remains incomplete. Microbial communities, under-ice ecosystems, deep ocean habitats, and isolated terrestrial regions all continue yielding new information. Some species likely remain undescribed. Others may already exist in museum collections awaiting modern analysis. Discovery unfolds gradually rather than dramatically. Technological advances support this process. Autonomous underwater vehicles explore beneath ice more quietly. Genetic sequencing identifies organisms from environmental samples. Satellite monitoring provides continuous large-scale environmental data. Each tool adds clarity without eliminating uncertainty entirely. Human presence in the Arctic continues growing slowly. Research stations, indigenous communities, shipping corridors, and occasional tourism all interact with the environment. Responsible management aims to balance activity with ecological stability. Collaboration among scientists, policymakers, and local populations remains central. Indigenous knowledge continues offering continuity across generations. Long-term observational experience complements modern instrumentation. Integrating these perspectives improves ecological understanding while respecting cultural heritage. Education about Arctic ecosystems is expanding. Schools, universities, and public outreach programs increasingly emphasize polar science. Greater awareness helps sustain research funding and encourages conservation-oriented policy. Ethical exploration principles discussed earlier remain active considerations. Minimizing disturbance, preventing pollution, and respecting fragile habitats guide research design. Advances in non-invasive methods support these goals. Climate modelling depends partly on Arctic data. Understanding carbon cycling, ocean circulation, and ecosystem feedback improves global environmental predictions. Polar research therefore contributes far beyond regional interest. The Arctic also influences atmospheric patterns affecting weather in distant regions. Studying these connections enhances forecasting accuracy. Again, incomplete biological knowledge intersects with broader environmental science. Long-term monitoring programs continue expanding. Ice-tethered profilers, acoustic arrays, permafrost sensors, and satellite observation networks provide continuous data streams. These systems reduce reliance on intermittent expeditions while complementing direct fieldwork. Scientific collaboration across nations has strengthened over recent decades. Shared challenges encourage cooperative research, despite geopolitical differences. Data sharing agreements enhance cumulative understanding. Public perception continues evolving. Earlier images of the Arctic as empty wilderness are gradually replaced by recognition of complex ecosystems. This shift supports more nuanced environmental discussion. Museum archives, historical records, and modern field data together create a layered understanding of Arctic biodiversity. Retrospective analysis often reveals patterns not obvious initially. Discovery therefore occurs both forward and backward in time. Technological optimism remains balanced by environmental realism. Tools improve observation capacity, yet natural conditions still impose limits. This interplay keeps Arctic science grounded in practical experience. Funding stability remains essential for sustained research. Long-term projects provide insights unattainable through short expeditions. Continued public and institutional support enables consistent observation. Future research priorities include understanding ecosystem resilience under climate pressure, documenting remaining undocumented species, and refining ethical exploration practices. These goals overlap rather than compete. The Arctic also serves as a reminder of scale. Earth's biosphere contains regions where human observation is still partial despite advanced technology. Recognizing that limitation encourages scientific humility. Curiosity remains a positive force when paired with responsibility. Exploration driven by respect rather than exploitation tends to produce both knowledge and preservation. As environmental change continues, the Arctic will likely remain scientifically significant for decades. Ongoing monitoring, interdisciplinary research, and community collaboration will shape understanding progressively. What emerges from all of this is not a conclusion in the traditional sense. The Arctic remains active, complex, and partially unseen. Discovery continues quietly through data collection, careful observation, and collaboration rather than sudden revelation. For anyone listening from far away, perhaps in a warmer place, perhaps late at night or early morning, it can be reassuring to remember that some parts of the world still move at slower rhythms. The Arctic changes, but it does so in ways that invite patience. Scientists return year after year. Instruments gather data quietly under ice. Communities observe seasonal shifts, and ecosystems continue functioning largely out of view. And somewhere beneath that ice, within frozen soil, along dim ocean layers, or across distant tundra, life continues in forms both familiar and not yet fully understood, carrying on in that steady, unhurried way that keeps the Arctic, even today, a living frontier of quiet mystery.